Bonjour, bienvenue à l'Institut Quantique. Welcome to this, first symposium that the Algo Lab is organizing. We have a great lineup today. Very happy to have you all here. There's about, I don't know, 70 people maybe in the auditorium right now, and probably as many online. So before we start this day, I have to say that if you have parked somewhere on campus, the parking is not free, and you have to pay with the BCD application. First thing. Other than that, I'm very happy to have you here. We have a great lineup today of people talking about research in quantum computing. As you have probably seen on the schedule of the day, there's three main parts during these presentations up to about 2:30 this afternoon. First part will be, presentations of research projects in quantum computing. We will have, I will call them flash panel discussions because they will be short. There will be intense discussions with partners that we've been working with and that are actively working in quantum computing. We will also have some hardware providers coming here, talk to you about their systems, their approach to quantum computing, and we will see these three parts coming again and again during the day. And at the very end of the day, we also have, for the people that are already subscribed to our reading groups, these breakout sessions, and also a discussion about education and more for people that are here on premise at Institut Quantique. So before we go further, let me introduce myself. I am Hossein Sadeghi, manager of the Quantum Algo Lab here at Institut Quantique, also in charge of the partnerships. And I would like to welcome Professor Stefanos Kourtis, who is the scientific director of the Algo Lab. He has a few words for you.
Bonjour, merci Hossein. Good morning, everyone, and thank you for being here for this first symposium on applied quantum computing. A couple of days ago, I asked Tom and Ghislain to give me some statistics on the number of projects that on quantum computing that are ongoing at the Algo Lab to compare with the situation when we started. So when we started 4 years ago,
almost five
years ago, we had just a handful of projects. Whereas today we are at more than 25, around 27 ongoing projects on quantum computing. At the same time, we have a diversified ecosystem. You see all these logos here. We have access to various quantum computing architectures, and we have access to talent that descends here in Sherbrooke or generally in Quebec. And we have a series of initiatives coming either from the government, the federal or provincial. We have the private sector also being involved actively in developing this ecosystem. And of course, the university and the researchers that are more and more interested in understanding what it is that we can do with these machines that are in a technological level that is very interesting today. Okay, so in the context of all of this, we organize this symposium on applied quantum computing to bring everyone together to exchange, see what's possible, spark new collaborations, and generally shape the future of quantum computing here in the region, the province, the country, and globally. So with that, I welcome you again. I hope you have an enjoyable day and stimulating discussions.
Great. Thank you, Stefanos. I would like to thank District, the Quantum Innovation Zone here in Sherbrooke, for the sponsorship of the breakfast we had here on premise. So if you are online, or hopefully next year you will come here and taste next year's breakfast. A few more words about the Algo Lab. The Algo Lab is a special beast here at the university. It is what we call a platform. There's about 20 platforms within the university. The Algo Lab is one of them. And the Algo Lab is the one dedicated to quantum computing. And what a platform is at Université de Sherbrooke really is a shared resources for anybody who wants to do research using the services that are provided by this platform. So in the case of the Algo Lab, of course, we work with various groups within the university in bringing quantum computing to their research. And this is part of what you will hear today. There's many projects that we've worked on the past years that will be presented to you today. And we don't do that only within the university. Last year, it was about 14 groups within the university that we worked with. But we also work with external partners. Many of them are here today. You can see the logos of the people that will come here and talk to you. There's many more, but like for now, this is the lineup for today. And it is very important to us to bring the industry to quantum computing and the quantum computing to the industry. We want really to, since it's applied quantum computing here, the idea really is to see, okay, how can we bring this new tool? How can we bring this new way of thinking about computing, these new paradigms of computing to problems that are met in the industry, and how can we think with these new things, with these new tools in solving the problems that are in the industry and get these new ways of solving them. So it's the general idea of the Algo Lab. And we are very excited to, present all of that to you today. I will have the hard task of timekeeping, and I can tell you that it will probably be very brief, and the presentators will all come to me at the end of the day telling me that they didn't have enough time. I can already tell that this will be in the evaluation forms, and it will also be true for what we call the flash panel discussions, because people will want to talk way more than the time that they will be allowed to. I can already tell you, but this is the way we designed the day, and hopefully it will be very lively, and it will bring some kind of like dynamics to it that will be of interest. And of course, if there is any presenter that talks about something that is of interest to you, please do contact these people afterwards. And it can be at the end of the day with the 4 that we're going to have, or can be like by email afterwards, or whatever the mean you'd like to use. But please go contact the people you would like to talk to. This is the whole mean of this day today. So let's start the day with a first presentation on a actual project that is taking place here with many different partners. So I welcome Jean-Frédéric Laprade, member of the Algo Lab, quantum software developer at the Algo Lab, come to talk to you about anomaly detection in communication channels. This is a project with Thales and also with Polytechnique Montréal, with Zetan, and of course, Université de Sherbrooke. So Jean-Frédéric, you can have a mic just over there.
Thank you, Ghislain. Hi, everyone. Thank you for the opportunity to present our project, Quantum Machine Learning for Anomaly Detection, which is a partnership between Thales. Zetan is a Montreal-based startup. Professor Soumaya Cherkaoui, which is here at Polytechnique Montréal, Professor Xingyi Wang from Université de Sherbrooke, and the Algo Lab at Institut Quantique. Changer les slides avec ça. Okay. Okay, so very briefly, the project overview. So the goal of the project is to design and develop a framework for network anomaly detection using quantum machine learning. It's a 3-year project that started November 2022. So we're already 2 years into the project. And it covers 3 different research tracks. So the first track is about designing quantum machine learning architectures for network anomaly detection. Second track is about identifying classical network data feature that facilitate the quantum advantage, or if you put it differently, identify data feature in network data that are suited for quantum computation. And the third track is about using generative model to do network data augmentation, mostly with quantum GAN. So this project is the hard work of so far 4 master's students and 5 PhD students. And I will try in the next 5-6 minutes to give you a brief overview of 3 of these projects. Slide. Okay. Oh. All right. So the first project, QuackTSF. So QuackTSF stands for Quantum Classical Kernelized Time Series Forecasting. So it's about time series forecasting, where we want to use a Gaussian process regression. So essentially here, X is a time series up to time t, and our goal is to model a function f that can predict X at time t plus 1. Okay? And we do that by the model that we use is a Gaussian process. So in this case, f here is the Gaussian process, and f of x is a random variable that is characterized by the mean and the variance, so that we can express through a kernel. Here, the kernel is essentially a similarity measure between 2 points, here x and x prime. So when we do that, of course, the choice of the kernel has a big impact on the type of function that you can model. So what we did in this project is that we implemented a quantum kernel. So we can do that on the quantum computer. We have to define a unitary for data embedding. So in this case here, it's the U that you see, okay? And this, we can implement that efficiently on the quantum computer to compute this kernel. Why would we do that? Well, the idea is that if this unitary is classically intractable, then it could give us access to like new class of function that could not be available through classical means. So for this reason, we use the IQP feature map for this project. And very briefly, what are the conclusion of this paper? Well, we compared our quantum kernel to 4 different classical baseline. And we see that in general, the prediction obtained with the quantum kernel, they align well with those generated with classical kernels. But interestingly, it produces a smoother and slightly different curve for mean prediction. What I mean here is that I have just a comparison with one other classical kernel, which is the RBF kernel. And as you can see, the mean is the kind of the blue curve in the middle. So it's the peak here, it's smoother than this one here. And this was observed for all the different 4 classical kernel that we use. So it's just the take-home message I can take is that it seems that this quantum kernel offers a different way to look at the data structure. So we could see it as a new tool in our set of tools when we want to do machine learning. Second project, latent QGAN. So the idea here is to do a quantum generative adversarial network. So for those of you that are not too familiar, again, the idea is that you have a discriminator, and a generator. The generator is responsible to reproduce, to mimic some real data sets or distribution. And the discriminator wants to discretize between generated data and real data. So it's an adversarial game that you play when you train this cost function. But so QGANs are present in the literature. There are many challenges, and how they were addressed in this paper is that for the size of the generated data by the generator, we use patches. So we have multiple generators that specialize in different parts of the data. Then to introduce nonlinearity in the process, we use ancilla qubit with post-selection. And finally, to map the generator's output, which is essentially a distribution over a probability amplitude. We use an autoencoder to map this distribution to a distribution that looks like an image, because in this case, we use images. So the result, this was trained on MNIST 28 by 28, which were compressed to like 40 latent space of dimension 40. We trained 5 quantum generator, 4 qubit each. And this was trained on real hardware. So this was trained on IBM Quebec. So what you see here, this is the general architecture. I will not go into the details here, but what you can see, this is like the real MNIST data set. And for example, the third line here is the result that we obtained on the real hardware. And maybe next slide. And the last project, very briefly, it's a conditional GAN. So in this case, it was to do anomaly detection with a GAN. So here again, we use the generator to generate new next data point in the time series. And then we see if it's close or far away from the actual from the true value. And when it's the case, then we can flag it as an anomaly. But in this case, what was interesting is that we used a continual learning. So it means that when an anomaly is detected, then the model is allowed to train again on the data that keeps going in the model, so we can adapt to new regime. As you can see here, where the blue is the real data, and the orange is actually the generated data. So next slide. So ongoing and future work, what we want to do is to identify some structure present in the network data that are suitable for quantum computing. So of course, this is a very broad objective. Build on our experience with QGAN to train generative models for network data augmentation. And finally, we want to identify new QML architectures that address the many problems of the field, such as barren plateaus. So there are many challenges with QML methods. So this is something that is very of interest to us. And maybe we can go to the last slide. So to conclude, thank you very much. This is part of our team that were at the IEEE Quantum Week conference last fall. So thank you very much.
Thank you, Jean-Frédéric. Right on time. Thanks a lot. That was perfect. You will hear more about this project, I guess, in the next panel discussion that comes after the next presentation with Soumaya Cherkaoui, who's going to be on the panel. So next to talk about still quantum machine learning projects in quantum computing, Marco Armenta from the Algo Lab as well will come and talk to you about another project we had with an external partner. It was, in this case, Natural Resources Canada. Marco?
Hello. So this is more than quantum machine learning. Is like interaction between AI and quantum. And this is a joint project with the Natural Resource Canada. The main contributor here was Adam Smith, who's a master's student in the University of Calgary. And here, a little bit of a background on machine learning, because this is hyperparameter optimization of machine learning models. All right. Now, a couple of things you need to know about machine learning models is that you have two types of parameters. You have the model parameters that you train, for which you use the data set to get better parameters at each step. But there's also hyperparameters. And now the thing is that when you do the training, you get your data set, which is usually a huge data set. You partition it into two. You call one of those the train set, usually the bigger one. And then you do this part, the model training. And this is very costly because you have to pass the whole data set through a big machine learning model several times. And just to give you a few numbers, for a ChatGPT, one of these things costs around $4 million. So this is a very expensive process. And you're not done with just one of those. You have to do several because there's some hyperparameters that control the training. There's things like learning rate, batch size, optimizers, which change the performance. So the performance of this machine learning model depends highly on the choice of hyperparameters. And then there's a few ways in which you can do hyperparameter optimization. There's random search, grid search. One of the most used is Bayesian optimization, but this is very good for continuous variables. But we do have some hyperparameters that are discrete. Now, so the idea was to use genetic algorithms inspired by quantum processes. And the idea is that you start with a population, and the thing is that to do something that resembles natural selection. So you start with a population of hyperparameters, and then you do evaluation of the fitness function. And this is basically done by training the machine learning model and evaluating it. That gives you a value that I'm going to tell you exactly what this is later. And then based on the performance, you decide if you stop or not. And if you don't stop, then you do this process. So this is selection is you take the hyperparameters that give you the best performance. Then you do crossover, which is basically you do like a mating of the hyperparameters that were chosen there. And then you have a mutation process, which is random. Now, the task was just binary classification in our case. It came from a data set from the Center for Canada Mapping and Earth observation. So in this case, it's just a prediction of flooding. The data set has 7 features, and we have around 345,000 training samples. And it's all across Canada. And in this case, so the data set comes from CCMEO. And the data set has things like proximity to water, elevation above water, slope, etc. Things that you will consider to be important for these kind of things. The machine learning model was pretty simple because we wanted to run this several times. So this was just a multi-layer perceptron that more complicated things can be done. So the things that we write was the model size, the number of layers, the number of neurons that were on the neural network, the batch size, which is how you sample the data set, the learning rate, the optimization algorithm. And this is the fitness function. Now here, lambda is a parameter that we did a couple of samples and we decided to put just 1/2. And here you have two important things. You have V, which is the validation loss, and epsilon, which is the training loss. So this gives you a measure of how good your model performs after the training. And we did everything is average on the last 10 epochs of the training process. And here are some results. We implemented 5 algorithms, from which the last 2 are classical. So the red one is classical genetic algorithms. The last one is Bayesian, which is what is mostly done right now in machine learning. And these are the generations we produce on the population. And you can see that with less generations, the quantum performs slightly better in terms of fitness. But after a couple more, they perform mostly the same. And one of the important things is that in terms of fitness, they perform mostly the same. But in terms of accuracy, you see that we outperform Bayesian, but just a little bit, right? So here you can see always the Bayesian one is down below. In terms of generalization, the Bayesian is better because these things are close together. And that's it.
That's good. Good. So thank you very much, Marco. Good. So This is the first time we're going to use this format. So the idea here is to have a flash panel. So I'd like you to think of it more like a hallway conversation, more than a presentation. So let's discuss all together about, well, quantum machine learning aspects of quantum computing projects. And but first of all, of course, I would like to know who you are. So if you want to start first, Ola.
Yeah, thank you very much. And it's my pleasure to participate in this symposium. So my name is Ola Ahmad. I'm the chief AI scientist at Thales Cortex Labs, Canada. I'm responsible of leading the research roadmap on trustworthy AI, including also AI embedded in critical systems. And I'm leading a team of scientists working on machine learning AI.
Good, thank you. Soumaya.
Hi, my name is Soumaya Cherkaoui. I'm professor at Polytechnique Montreal. Actually, Sherbrooke is my alma mater, so I'm very happy to be here today. I work on the convergence of AI and communication networks in general, and they have been introduced to quantum machine learning, quantum computing about 4 years ago. And it has been an exciting journey for me.
Good, thank you. And Asif, yeah, we're going to share the mics.
Thank you. Hi, everyone. My name is Asif Iqbal. I'm the Senior Policy Advisor at Office of the Chief Scientist and Natural Resource Canada. So as the lead for Quantum, I oversee our collaboration with academia and industry. I'm also managing a small team of quantum experts. So we're working on some quantum R&D projects. Happy to be here.
Good, thanks. So maybe, Soumaya, we can start with you. Jean-Frédéric has talked a bit about the project that we've been all working together for many years now. So well, 2 years on the actual project and 2 more before that in designing the project and getting the funding for it and all. Can you tell us how you see quantum computing, well, of course, using quantum machine learning in your case, in your research? How does it integrate into what you do like for many more years than that?
I see many opportunities actually, and many challenges also. I see quantum computing, quantum machine learning as the next frontier. Obviously, with the kind of data we work with, there are many challenges, but I think the results we have obtained right now are very promising. So I'm just excited to the next, level when the number of qubits available, the capabilities of computers grow. I think that it will be an even more exciting journey.
Good. And Ola, on your side, how did you get involved working with Thales in the project with Soumaya and University Sherbrooke and Zetan as well?
Yeah. So the idea is, first of all, Thales plays a very active role in cybersecurity. And so, for example, here the project is about network anomaly detection. It's for cybersecurity, And this is how we got involved. It's because we wanted to get into the ecosystem from its beginning. We know this is an emerging technology that has a lot of promise, and we want also to explore and be part of it. So this is how we get involved in this project through INSERC program. And yeah, we collaborate together.
Good. And Asif, on your side, you are at Natural Resources Canada. We've been working together as well on a project using quantum machine learning. How have you been involved in the project?
Oh, that's a great question. So I think we're still in exploration right now. So one of the things that I'd like to mention that our department, we have energy, natural resources, Earth observation, geological survey, all those are part of our mandate. So we see quantum technology will impact our sectors. And one thing that we know, at least from literature, that these sectors are among the sectors which will have, near-term benefits from this technology. So we'd like to explore that. And one of the examples I would refer to, like in the work that we, collaborated with Aglo Lab and University of Sherbrooke, and Marco just presented the work. So I think we see enormous potential here, but I think we are looking for more of, finding the economic value of those projects, like how those projects can bring impact for our sectors, for Canadians. So those are our, our motivation, our objectives. But I think, as other panelists mentioned, that as we see more and more qubits coming up, I think we'll be exploring more of this technology for our sectors.
Good. And Adam Smith, who was part of the project as a master's student, he started here. Well, he was from University of Calgary. He's been involved here with the AlgoLab team, and then you hired him at Natural Resources Canada. So I mean, it's a successful story here, seeing a student that works with industry, well, in this case Natural Resources Canada, then goes to your organization afterwards. So how do you see growing the capabilities within Natural Resources Canada in terms of quantum computing?
So right now, of course, like one of the challenges that we are facing is to find the right expert to solve some of the problems that we are dealing with. And of course, we're relying on all these ecosystems that are developed like within Canada. I think it's still a challenge, and we don't want to honestly like develop like our, quantum team internally, but we'd like to rely on the resources that are available through our ecosystem. So that's the short answer, but I'd like to add more. Like I know like there are other students like from this institute, like we worked with, they're part of our, quantum R&D projects in many capacities. For example, like as an intern or like, research scientist. So yeah, so that's the, I would say like the model that we've been taking, at least for now. And looking forward to more of this collaboration.
Good, thanks. And Ola, Thales, of course, is a multinational company. I think that you have teams in France that are working in quantum, well, probably more even than here in Quebec and Canada. Can you talk about how you see your, internal capabilities within the company in terms of quantum computing?
Yeah, actually, you are right. In France, we are working on very big, my colleagues who are working on very big project. It's about, it's called BAC. It's the benchmarking application of quantum computers, benchmarking applications of quantum computers. This is how can I phrase it. So it's a big project that includes also a lot of partners from the industrial and academic ecosystem in France. So they are interested in exploring the advantages and benchmarking different quantum technologies. From our side on Canada, we are more on the quantum algorithms, like for example, quantum machine learning, quantum optimization. So there is a kind of synergy between what we are doing and
Good, thank you. And Soumaya, since you are working together on the project, how do you see your role in terms of course, talent development? Because I guess with the number of students that we saw, well, both from the master's degree and the PhD level, there's many of them that have been working, are still working in the project. So how do you see this role you have in terms of workforce development here?
I have anecdote to say about this. At the beginning, it was very difficult to hire students who would be willing to invest time to understand the technology, etc. The learning curve was very steep. But at the end, now this project has so many students working on it, but also other students in my lab, having seen what quantum is capable of, they're introducing quantum stuff in their own projects. So I think science like this, things that are being developed and have so much potential, there will be no problem in bringing more talent in to be able to develop the new things. the new generation of, scientists who will be doing new stuff.
And when you say that the learning curve was hard at the beginning, is it still as high now, or because the students are more in contact with quantum computing, then it gets easier for them to jump into this field?
Now it's much easier. At the beginning, the first students spent maybe just about 6 months just to start to understand what is quantum computing, what we can do, what we cannot do. But then the students that joined after, it was very easy for them because they are in the same lab, they interact with people like Jean-Frédéric, Olivier, and so on. It's very easy for them to, get the information easily, and they feel also somehow safe, because they know others have been able to do stuff, their colleagues in the lab. So I'm very optimistic.
Well, thanks. And if we come back to, quantum machine learning itself, of course, you've been working in machine learning, classical machine learning for many years. So how do you now envision those projects? How do you add new ways of using quantum computing? Because of course, quantum machine learning is very broad. There's many, many approaches. Some we know now don't work. Some are more promising. So how do you choose what next steps are?
I think the future will be hybrid. As we understand quantum technology more, we are able to identify problems where quantum will probably give an advantage, and other things, probably machine learning, the regular one, or other methods will be more efficient. So yes, I mean, we get into that space now where we can see, this will be very difficult to do in quantum as far as the capabilities that are available right now. And these other things, probably there will be a big advantage. So let's, put our emphasis there. So I think the future is hybrid, definitely.
And Asif, if I come back to you, what's the future, in quantum machine learning or more broadly in quantum computing?
Yeah, I mean, I'll just add what Soumaya, you mentioned. I think, and going back to the last question that we asked, so in our R&D projects, you were part of that discussion as well. So one thing that we did, we actually reach out to our scientists, and since they are working on many sectors, they are expert of many things, but not quantum. But they had these problems that we believe that some of the solution of those problems can be done by existing quantum techniques. So what we did, we shared those problems at a very high level to our experts. And get their opinion, like what can be done in which timeline, and then basically determine the scope and deliverables of those projects. So I think we all need to come together and kind of work around that, like what is possible given the technology, it's still under development, but there are potential. And I also believe we need to find out this winning, use cases. And also maybe like the hybrid technique could be something that we can explore for now, and wait for the full-scale quantum computer being available to do all this cool stuff.
Great. And Ola, on your side, what do you envision for the future?
I'm also optimistic. It would be very nice to continue collaborate with our ecosystem, academic ecosystem, in order to advance research and also get engaged in more fast, let me say, because as you mentioned in the beginning, we need to bring industry to us and vice versa. So this is what we also are looking for. I agree with you, it's very hard to find the use cases that are relevant right now, but we need to continue explore and see what we can do. We know the limitations right now, so I think in the short term, it's like continue advancing, developing quantum algorithms for the, let me say, the constrained computers right now. But I hope that we will also, let me say, in the future, we'll have more efficient, scalable computers that will be able to handle complex problems.
And what do you see? What do you see the best way right now, or the best projects are right now? Is it like more theoretical and fundamental for the day that fault-tolerant quantum computers are
We need
present?
to
Or
do both. We
Yeah.
need to do both.
okay, so still working on
Yeah.
what can we do with the systems right now,
Yes.
and what can we take out of them
Exactly.
as we speak with
Yeah.
the current systems.
Yeah, we need to balance both of them. Yeah.
Okay, and how do you choose the projects? You were saying we have to choose and continue working on projects. So how do you well select the projects? Of course, within the actual project with with Polytechnique Montréal and Université de Sherbrooke, or like in France, your colleagues that are still working on quantum computing.
Yeah, so the choice of the projects is based on what kind of complex problems we want to solve that are more close to what our business lines are looking for. So sometimes it's very difficult to find this kind of synergy. And this is why sometimes we try to say, okay, let's explore this like a kind of more, it's push technology than pull technology, let me say it this way. So we need to explore things that even if our business line is not ready now for it. And this is why we collaborate with our academic ecosystem. It's for this reason. So yeah.
Good, thank you. I would like to turn to the audience now. Do you have questions for our panelists? And it can also be online. If people online would like to put questions in the chat, we can also have that way of doing. Yep. Yeah. Well, there you go.
How do you see your program developing over the next 6 months and then longer?
Yeah, like for example, for this project, I think we will go towards a hybrid in the short term. There are also other ideas, bubbling, now that we know very well what quantum computers can do or cannot do at this stage. There are other things, other ideas about new development that we could be doing. Obviously, we will not talk about them right now because they are not materializing yet, but they are in preparation. But for the short term, it's going hybrid.
Okay. Questions online? Okay, so there's a question online about cryptography or post-quantum crypto. Do you have anything to say about this, even though it's not exactly the topic we were talking about?
This is the kind of thing where I say quantum is contagious. Like some people in my group are starting to look at this without being involved in the project, for example, with Thales. Now they understand what are the different flavors of quantum, like quantum communication, post-quantum cryptography, and so on. So they are trying to see how it can fit in that project. And they are almost all of them, even if they are not in this quantum project, they are trying to go there. So I think it's an exciting technology in all fronts.
Thanks. Yep.
Are there any considerations of safety or alignment already in this work, or is it too early to talk about that?
I think it's a bit early. Yeah. In the project that we are collaborating on, we don't have this kind of problem right now. It depends what kind of alignment you want to address. Alignment with what with human needs, with so yeah, so far we don't have this problem right now, and I think it's a little bit early to talk about it because we still are, let me say, addressing the limitations of quantum computers right now. So I think it's early.
And if I'm not mistaken, you publish the work that you realize, right? And I know there's been many articles written that are from this project. Do you want to talk about it, Soumaya?
Yeah, so basically, Thales and the other collaborators have been very, forward into, allowing students to publish their work, and where this is a very great. I mean, from the perspective of academics, this is great because we are allowed to share our findings, etc., and also bring in new information from other, ecosystems where quantum computers have been used. So yeah, so all the papers regarding our work are online, and even prior to publishing, we put them on archive, for example, where they can be looked at. So well, I would like to thank Thales for this actually, because they are allowing us to do this.
Asif, any word on that?
Yeah, I mean, from our side, what we can say, like we have very, defined procedure of like working on the projects, which also safeguard, data related to the projects, IP, and many other things. And I think around that, I'll also echo with you guys that, we are encouraging, publication through our projects. So yeah, it's mostly, working through our procurement team, our IP team, our data team to find out like what is what we can share. And we are basically for this very specific early stage projects, we focused on open data so that everybody can see, the community can see like what we are doing and can be benefited from this.
Okay. Yep.
Hello, thank you for the presentation. I have a question regarding the industrial companies, especially in Canada, because we want to have them engaged into new projects, and we want to have them also more sensitized to quantum computing. So do you imagine, and what could be the programs and the actions to have more engagement from the industrial companies, and especially from those that are inside the Anarchian community?
So maybe I can talk a little bit about engagement and the programs. So what we do, like an industry from our side, is we try to address INSERC research programs like INSERC, MyTax, these kind of programs. And also there is programs, Canadian programs, like, for example, it's more like federal programs like the IDEAS or other kind of programs that we try also to address, let me say, to get engaged in order to be able to have some funds in order to investigate more, because yeah, it's sometimes difficult. And also the Ministry of Economy. So we try to go through different kind of programs in order to get more engagement. And I think Canada now is starting more like investing in new programs specific for quantum technologies. So it's a good, great opportunity I see.
Yeah, sure. So what I would like to add with that, so yeah, we have multiple program streams. I know like we have our colleagues from NRC here as well. They can speak to their programs, but there are multiple programs where companies, they are encouraged to work with academia and government as well. For NRCan, since we don't have any quantum specific program other than the quantum launchpad that we created a year ago, those are like pilot projects. So we don't have any specific quantum program yet, but that said, we are part of this initiative called QRDI, which is Quantum Research and Development Initiatives, where we are working with collaborators in industry and academia for long-term projects. But we also have some sector-specific programs. Those are not quantum, but we see like, for example, critical minerals, forestry sectors, their programs. So maybe there are some programs which are not specifically focused on quantum, but there may be a quantum application, and those programs could be something that the industry can work with our department and our scientists.
Good. We have maybe one last question that was online. Soumaya, we'll maybe start with you. The question is about, well, since you are working on autonomous vehicles, right? This is another part of your research. The question is about robotics and processes there. Is there any application you can envision for quantum computing or quantum machine learning applied to robotics? And I start with you just because since you're working with autonomous vehicles, maybe you have an insight on this.
Very difficult question. I guess when we are talking about autonomous vehicles, mostly it's about embedded technology. I don't think we are now at the level where we can embed quantum computers in vehicles. But I guess that, everything, reinforcement learning, that kind of thing that, has been explored in quantum, maybe they can, there can be new insights regarding that. Obviously, autonomous vehicles, for those of you who can, look at maybe the movies where, doomed future, where autonomous vehicles can be, the security concern, post-quantum, maybe cryptography, that kind of thing would be necessary in future. Also, autonomous vehicles are usually plugged-in vehicles. They have to be charged. They can be a threat for the smart grid. So there is a lot of quantum to do there, but not necessary in terms of autonomy, of the vehicle, but other aspects.
Good, thank you. Well, with that, I would like for all of you to have a great round of applause for Ola, Soumaya, and Asif. Thank you very much. I'm happy to see that it's harder for you to go quiet now than it was before when we started the day. That means that discussions have already started. This is great. Very happy to have you all chat with each other. I'm sure it will all continue over lunch. And this is great. This is exactly what we wanted when we worked on this day today. Now, let me introduce you to Alexandre Choquette. He's from IBM Quantum. And well, I will let you present yourself in more details and talk to us about what IBM has in mind in terms of development of quantum hardware. And I guess you'll probably talk a bit about software as well and algorithms.
So I actually took your instructions to the note, and I gave myself a challenge to give an IBM talk without presenting the roadmap. So there's no slide about the hardware roadmap. I'm only going to talk about software today. Yeah, okay, so I think you could, you know me well enough that you can even do the presentation by yourself. But yeah, so I'm Alex, and I work at IBM Quantum, and I manage our quantum partnerships across the country here in Canada. I'm based out in Montreal, but I am not a stranger to the Sherbrooke ecosystem. So I actually come from Sherbrooke also. I did a master's in quantum computing with Alexandre, who did not show up to my talk, so you're going to hear about that later. Yeah, and also worked as a scientist with 1QBit here in Sherbrooke, and also at IBM Quantum in Zurich. So funny enough, I just want to start with a very funny thing. I just came back from a holiday yesterday night where I was in Colombia. And people were asking me, oh, like, is work bringing you to Colombia or like going for holiday? I was like, oh, I wish work was bringing me, to Colombia, kind of as a joke. And then I noticed here on the board, it says Delegación de Colombia. So it was here. So I guess there are someone interested in quantum. So maybe next time I'll go for work. Okay, yeah, so okay, so the talk is titled A Quantum-Centric Supercomputing Approach to Realistic Formulation of Nature. And my goal here today is to kind of give you an overview of, from an IBM perspective, what is the state of the art in terms of what you can do with quantum computers instead of what quantum computers are in terms of like number of qubit and things like that. So I'm going to talk about two software results, or two kind of demonstration results that we have. And this is already not, it was working like a minute ago. Awesome. Yes. So, yeah. So it's going to be about what you can do, kind of what has been demonstrated, but also in terms of capabilities, and also where we see things going. What is kind of the grand vision for us at IBM? So the first results, I'm sure a lot of you have already heard about it. It's more than a year old now, but it's what we refer to internally as the utility paper. And so that is a Nature paper that came out in 2023. And kind of the main message, if we want to boil it down to one sentence, is that noisy quantum computers, so the ones that we have today in labs, they can produce accurate expectation values on large quantum circuits. So this is what quantum computers are good at, is to run very large quantum circuits, and we can get increasingly accurate results out of these circuits. And then the next results is more about a new paradigm or a new kind of architecture that we call quantum-centric supercomputing. I'll cover what that is later. But this new architecture enables realistic formulations of nature with pre-fault tolerant quantum computers. And this is a little bit more of a recent result by our team. And this is what we refer to as a QCSC, for quantum-centric supercomputing chemistry paper. So it's a very beautiful result, and I'll talk about that. All right, so let's start for the first one. So I'll go briefly, because as I said, I've covered that in a few talks already. But this was so that was the Nature cover that we had a few years ago. And so as I said, now we can produce, and through this work, we were able to get accurate and kind of satisfying results out of 127 qubits and running circuits that had close to 3,000 gates. And so back in 2023, that was kind of the state of the art. Now we have new chips, and we can run up to, say, 5,000 gates or 2-qubit gates on our quantum devices. And so to jump into a little bit of the detail, so what is the problem that we solve here? So this was a trotterized version of the transverse field Ising model. So it's a problem that, so it's a magnetic material problem, kind of a toy problem that physicists like to solve. And the important thing is that it looks like the type of problem that would be useful eventually. And what we're doing here is kind of a poor trotterized evolution. So it's kind of a time evolution of that problem. And we basically solve the problem on the hardware qubit topology that we have here. And then when you trotterize this Hamiltonian, then you get to a circuit that kind of looks like this. So we have layers of single qubit gates that encode the X terms, and then the 3 layers of CZ gates. And you actually need 3 layers to cover all the connections from the model here. And then we repeat that, I think, up to 20 times, and then we measure the state at the end. And so what we first did, so whenever you're trying to solve things at a very high scale, with 127 qubits, you unfortunately cannot simulate it classically. So, as a researcher, we like to have access to our simulator so that we can readily compare the results of hardware runs to the exact answer. But when you reach a certain scale, then you cannot do that anymore. You have to fold back to tensor network methods, for example, or approximate classical methods. So what we did for that work is we first scaled it down to go into a regime where we could still get the exact answer, and that's the gray line here on the plot. And then here we're just measuring some expectation values as a function of the X parameter, or the transverse field strength. And so what we do is we run the circuit, then what we get is the green data, and but this is noisy data, right? So we need to get rid of the noise, so we perform error mitigation, and then we recover the blue data that somewhat fit the exact data here. And at the time, this was a collaboration with our collaborators at Berkeley, and they were tensor network experts. And so they use what, to the best of their knowledge, was the best tensor network method at the time. And here we could see that, at low entanglement, so kind of towards the left side of the plot, the tensor network methods were very accurate. But these type of methods are typically not so great when the entanglement grows in the system. So this is why they started to crash when you increase the RX angle. So the goal of that kind of first step was really to gain confidence that the quantum computer could get accurate results, and then we could push it. So now we're tackling circuits that have 68 qubits or even 127 qubits, and we're measuring similar expectation value again as a function of the Rx angle. And what we get is the green data, and then we perform similar mitigation methods, and then we recover the blue data, and then we don't know, because there's no way to compare with an exact answer. So it's hard to trust anything there. We can do is compare with the classical tensor network methods, and they seem to be agreeing at low entanglement again. Then there's some disagreement as the entanglement grows. But one thing that we know is that at the extrema of this plot, the circuits are Clifford circuits, meaning that only at the extrema they can be simulated efficiently classically. And so we know that we're on the right, on the extremities of the plot, we're good. But yeah. So one notable thing here is that it was also faster to run this with the quantum, again, compared with these methods. I'll show you improvement in tensor network methods after. But a key thing is that, out of the, 9.5 hours that it took on the quantum computer, there were only 5 minutes spent on the actual hardware, meaning that most of the time is actually classical time to, control and optimize and do the error mitigation procedure. And since then, we have, I think I saw results recently. Since then, we have improved that by quite a lot, I think by like 50 times. And now you can run this whole utility scale experiment in, I think, 2 hours or something. So we've done like tremendous improvements into the classical software. Anyway, so whenever there's a quantum hardware company that comes out with a result, there's always a great answer from the classical community. And so, in the weeks and months following that result, then we have a lot of tensor network groups that came up with, results that computed the same thing, sometimes even faster than what the quantum did. But one interesting thing here is that none of these methods actually agree on like a specific or like quantitatively agree. And so that means that we still kind of don't know what is the exact answer to solve that one problem. All we can do is to plot all these methods and then draw some area of certainty. And interestingly, kind of in the middle of it, there's the quantum data that are here. So our argument here, our message is that we can now start to flip the script and for certain problems, start to use quantum computers to verify the outcome of classical methods as well. So that's, if you're curious, so these were the circuits that were run for the utility scale experiment. So you see the one block that I showed earlier, and there's like 20 of these time steps over 127 qubits. And just as a comparison, so this was the biggest circuits that we could run at the IBM Quantum Experience back in 2017. So there's quite a bit of improvement since then. And again, these are the circuits from a year and a half ago. Now we can run even much bigger circuits. So the message here is that, okay, like when we run these large quantum circuits, we can get accurate results out of it. Now, what about the second part? So the second part is about what if you couple a quantum computer next to a very large HPC infrastructure, and you make that coupling very tight so that they can exchange data very rapidly between both. Is there an advantage in doing so? And that kind of fits into like the IBM grand vision of what quantum-centric supercomputing is going to look like in the not so distant future. So eventually, we're going to have a few of these quantum computers all coupled together inside of all of these fridge. There's going to be chips that will be coupled together, and then we could connect the fridge by classical and quantum connection, and all surrounded with GPUs and CPUs to kind of work in an interplay between classical and quantum. And I just saw like literally 5 minutes ago, I think we came out with a new Nature paper today, where we're able to take two quantum chips that are, they live on the same plane, but they're coupled together, meaning that you can have periodic boundary condition or kind of simulate a periodic boundary condition on a chip, which is not something you can do with only like a 2D planar chip. Anyway, so we're making good results towards that goal. And then, so as I said, even that now that we have what we have in the quantum system 2s, or even the system 1, we have the QPUs that live in the fridge, but right next to it we have what we call the runtime cluster. So this is all the classical gear that makes the execution on quantum computers very, very fast, and you need this very physically close connection in order to be efficient. All right, so what sort of thing can you do with this architecture? So what the team kind of as a first use case to kind of demonstrate this architecture, they decided to work on a chemistry problem. So chemistry is one of the well-known use cases for quantum computers, and there was kind of a belief that pre-fault-tolerant quantum computers in isolation, meaning like only the quantum computer, cannot deal with realistic formulations of nature. And what do I mean by that? So let's look at some numbers. So if you take this fairly large molecule, Fe4S4, in this basis set that chemists might understand, this would map to 72 qubits. And if you write up the Hamiltonian, if you wanted to exactly measure the energy of that molecule, you would need to sample a molecule for 6.7 million Pauli operators. So it's a very, very big Hamiltonian. And say you want to reach a chemical precision for all of these, for the energy, so you need 10 to the minus 10 precision in milli-R3. Then you would need to execute 10 to the 20 circuits, or each circuit 10 to the 20 times. So if you wanted to use a pre-fault tolerant method such as a VQE, which is kind of known to want to tackle chemistry problems, then at 10 microseconds per circuit, that would take you 3 million years to sample the energy of that. So that's what we mean by realistic formulation of nature. So the molecules that are not the H2 molecules, they don't algorithms that we have today, like VQE, they don't scale super well. So we need to come up with new methods. And so that's why we came up with the quantum-centric supercomputing. And if we look at, so now we know for pre-fault tolerant, but what if you had a fault-tolerant quantum computer also in isolation, and you're trying to run, phase estimation, and that's the number of T-gates that you need, then it would still need, 13 days of runtime to, sample the energy of that molecule. And what we did here in this work is if we use this method called subspace estimation that I'll talk about later, then we could run the whole thing between in roughly 2 hours. And kind of the key to that result is that we kind of offloaded all the heavy duty work to the classical computer, because they're good at at dealing with a lot of data, and we only use the quantum computer for what they're good at, and that's getting accurate results out of large quantum circuits. All right, so what are these results? So first, the architecture that we use here is so one of the newer IBM chips, so the Heron chip that had 133 qubits, and we use up to 77 of these qubits, and for very large circuits of 3,500 gates. And the classical infrastructure is the Fugaku supercomputer that lives at the RIKEN lab in Japan, and we use, I believe, up to 1,600 nodes of that supercomputer. And the three problems that we solved, the first one was the N2, bond breaking diagram, and that in chemistry is known to be kind of a good example of if you want to benchmark a method, you try to solve the N2 bond test. And the main result is that the quantum computer was able to qualitatively reproduce the curve that we get with the heat back configuration interaction, which we found to be the most precise classical method for this type of problem. And but other well-known classical quantum chemistry methods were kind of crashing. And that was using 58 qubits. Then we tested it on Fe2S2 with 45 qubits, and we were able to find 3 eigenstates of the molecule here. That are kind of showed here. So here's it's a classical quantum chemistry method that we adapted to quantum. You're basically plotting the energy as a function of the variance of energy, where you have a tuning parameter that controls the accuracy of the method. And if all the data line up in a linear fashion, then you know you found an eigenstate, and you can draw a line through this and get to the zero variance and see what the energy is. And so we were able to get results that sometimes compare to DMRG, which is a very powerful classical method. And then just to see if we could push it a little further to test it at scale, then this is where we tackle the Fe4S4. And of course, the results were a little bit noisier than with the Fe2S2, but we could still find some eigenstates in a fashion that was better than some classical methods. And we compared it to just like a random distribution, and we found that we were actually finding accurate results. All right, how do we do that? So the key to this method is kind of two parts. One part is we needed kind of an HPC estimator that could take the data coming out of the quantum computer and extract some physical property out of it. So that's the classical part. And then we needed a class of quantum circuits that would be good to capture the ground state of the molecule. So for the first part, so this estimator that we use here, it's good because we can measure millions of Pauli operators very rapidly because they all live in the classical computers. It's good for ground state estimation because a little bit like Varchinal algorithms, we get always an upper bound on the energy, so we cannot find energy that's lower than the ground state energy. So we say that there's no false positive. It also uses, as I said, HPC. So the more nodes you have, the more like classical parallelization you can do, the faster the method is going to be, and the more accurate it's going to be. And similarly to error mitigation, there's a runtime that's exponential in the noise strength, meaning that if we reduce the noise, then we get also exponential advantage in the runtime of the method. And that's an important thing to note here is that we did not use any error mitigation on the quantum computer. All the noise was mitigated as part of this classical estimator method, and I'll dive a little bit more into that. And this method is good for Hamiltonians that have a concentrated waveform for the ground state, or if the ground state is quite sparse. All right. So what is this method? So what we do is we run the quantum circuit, and we prepare the state psi, which we hope that encodes the ground state. And instead of measuring expectation values of Pauli operators, all we're doing is just sampling the quantum computer and just collecting all the noisy bit string that come out of it. So we're generating this very large body of data that gets eventually transferred to the classical computer. So this is where the advantage of having the classical and the quantum being very closely tied together helps, because say you're running a VQE, you're transferring very little data between the quantum and the classical. It's only a few parameters one way and then expectation values the other way. Here we're transferring large bodies of data. And of course, you get all these bit strings, and some of them are noisy, meaning that they don't have the correct number of ones in the in the bit string. And so what we're doing is we kind of randomly flip some of the bits so that they all have the correct number of ones. And then we take all of this very large body of bit strings, and then we separate them to create different subsamples or subspaces. And then we project the Hamiltonian into these smaller dimension subspaces. And then we solve all these Hamiltonians in parallel using the classical parallelization capabilities. So we are actually diagonalizing smaller, many smaller Hamiltonians instead of like one very large one. And then we collect all these ground state estimates of these large, smaller Hamiltonians, and then we collect, for example, the lowest energy. That's what we're looking for, and also the average occupancy. So like how many ones there should be, and then we reuse that in the next iteration to flip the appropriate number of bits. And we can run this procedure in a self-consistent way until we reach convergence. So just to show you what the infrastructure looks like, on the one side you have the quantum computer with all the all the proper control electronics that you want, and then on the right side, this is where the classical computer is with this subspace method. So maybe just to give you a short example so that you understand a bit, and I'm doing like 1 minute, maybe 5 minutes. Okay. So yeah, so you prepared that. So say you're running this on 4 qubits, okay? And this is ultimately the ground state we're looking for. We know there's, it's 1100 plus 0011. There's only 2 excitations in the ground state. Then we measure, we get all of these bit strings. Some of them have the wrong number of excitation, but that's fine. So we just flip randomly a bunch of these bits, and then we split it and we create these different subspaces here. And then for all these smaller dimensions subspace, we again diagonalize, get the ground state energy, and then the average occupancies, and then we reuse that to in the next iteration to flip again the next bit string. And this diagonalization happens like that. So you would take the subsample that you had. So you have these 3 basis vectors, and then that form a basis, and then you can project the Hamiltonian in this way in the basis of these 3 basis vectors, and then it's an easy diagonalization to do. And if you had the right bit strings, then the ground state is going to be the right ground state. All right. So what circuits did we run to get that? So the class of circuits that we use are called local unitary coupled Jastrow operators. And so when you're running chemistry or trying to solve a physical problem on quantum computers, there's always these 2 paradigms of what type of circuits you want to use. So on the one end, you want to have physically motivated circuits because they're believed to capture more efficiently the properties of the problem that you want to solve. But sometimes they can get way too big for the current hardware, or even for fault-tolerant hardware sometimes. And on the other end, you have hardware-efficient circuits. So these are circuits that are basically you forget about what problem you're solving, and you just run a circuit that is the most efficient for the hardware. But it also comes at a cost of accuracy, so it won't be as accurate as physically motivated ones. And the cool thing with these LUCJ circuits is that they kind of sit in the middle. So we start from a physically motivated circuit that is the UCC SD ansat, and then we kind of modify the ansat to make it fit or map to the hardware itself. So instead of having to do a lot of swap operations to make sure to encode all the UCC-SD operators, then we just remove the interactions that for which we would need swaps, and just call it the ansat like that. So they map to these terms here, and that's the circuits that we ran for the so that's for the N2 circuits. So for the 52 qubit experiment. So you see the first orbital rotations at first, and then the Jastrow operator in the middle, followed by the rest of the orbitals. So this is what we mean by kind of local circuits, because they map very well to the hardware. And then you eventually need to map your molecules to the hardware, and so this is how we map the three different molecules that we solved. So with the 58, 45, and 77 qubits, we had some ancilla qubits that were helping to couple the spin-spin interactions. Yeah, and so the kind of the main takeaways from this work is that there is an advantage in terms of the runtime, but also accuracy in using this quantum-centric supercomputing architecture that we have. And also, this is only a first example of a chemistry problem, but we're looking forward to see what other type of applications we can do with this paradigm, because in principle, it's kind of a general framework, how to use this hybrid method. So we're also looking forward to new applications of that paradigm. Okay, I'll leave the rest for that. And there's the archive paper over there if you want to have a deeper look at the results. And then I'll just finish by saying that, every time we come up with the nice results, people are always saying, oh yeah, but this is the type of thing only IBM can do because we have the tools and you guys don't. So we're trying to change that. There's a little bit of that, but we're trying to change that. And for starters, we came up with this Qiskit add-on packages. So this is prepackaged code, prepackaged code that helps you program more efficiently so that you don't have to reinvent the wheel every time. And this exact method that we use, the sampling-based quantum diagonalization, so that box here is now available as a Qiskit add-on. It's called the SQD, and it's open source, and so you can have a look with that. And also, the important thing is that you don't need to have access to the largest supercomputers in the world in order for this method to be useful. Even with the small parallelization on a laptop, you can already start to tackle some smaller problems. Yeah, that's what I do. Thank you.
Thank you very much, Alexandre. We are going to talk to each other again in just a few minutes for the next panel discussion.
Absolutely.
So thank you very much. While Olivier Nahman-Lévesque is coming on the stage, Olivier is also from the AlgoLab team. You probably noticed that we moved from quantum machine learning projects at the beginning of the day to simulation of materials. And this is what Olivier will talk about as well. So Olivier, I guess you get a mic on the table over there, and the floor is yours.
Hello, can you hear me? Yes, I can hear myself. Okay, so my name is Olivier Nahman-Lévesque. I'm another member of the AlgoLab, and I'm going to talk about a project that we're doing right now in collaboration with IBM, where we're trying to measure state response functions on an IBM quantum computer. So a couple of months ago, IBM came to us and they asked us if, as part of their utility scale endeavor, if we had any projects that we thought would be interesting to run at large scales on quantum computers. And this is the project that we came up with. Prochaine slide. Ah, c'est moi qui contrôle. OK. Okay, so a quick description of the problem. So we are given a Hamiltonian, H, which describes some physical system, okay? And this is given in terms of like a sum of polystrings, for example. So we have a classical representation of this Hamiltonian. And we're interested in measuring a response function, for example, like the two-point propagator, for some interesting state psi. Okay, so the state psi, it can be, for example, the ground state of H, or it can be the lowest energy eigenstate in some like symmetry sector, for example. But yeah, so we have a specific state psi, and we want to study some of its response functions. Algorithmically, this involves measuring many expectation values on psi. Okay, so we have a list of operators, and we need to measure this quantity here, which is expectation values on psi. And again, we're trying to run this for utility scale problems. Okay, so a very large number of qubits, problems that are intractable classically, ideally, of course, but in practice, it's not so easy. And there's an obvious problem here is that you need an efficient way to prepare psi on the quantum processor. So this is like a emblematic problem to the field of quantum computing, right? I give you a Hamiltonian and you need to prepare like some interesting state on your quantum computer, like the ground state, for example. This comes up everywhere all the time. And there's many methods that exist, but a lot of them are outside of what current quantum computers, quantum hardware is able to do. So like many fault-tolerant algorithms exist, for example, but we don't have access to those, unfortunately. Here is an example of like some Hamiltonian that we're interested in studying, for example. So this is the Heisenberg Hamiltonian. So it's just spin-spin interactions on nearest neighbors on a lattice. Okay, so for certain geometries, this like the problem that we're trying to solve for this Hamiltonian is intractable, classically. Okay, so what's the solution? Well, we can't prepare the exact ground state of psi. This is too hard, as I mentioned. Okay, so we're going to do a little bit like what Alex was talking about in his talk. So we're going to use subspace methods. What does that mean? Well, we're going to try to prepare an approximation of the ground state of H in a certain subspace. So specifically,
we define a subspace of the full Hilbert space where the Hamiltonian lives, and it's called the Krylov subspace. And we're going to try to project the Hamiltonian onto this low-dimensional subspace, and then find the ground state of this easier Hamiltonian. Okay, we're going to try to do this classically. And so what do we need the quantum computer for? Well, the quantum computer is used to calculate these projection amplitudes here. So the psi here is a basis for our subspace that we've chosen in a smart way. And we're going to measure these projections on the quantum computer. And this can be done, it's not too complicated to do on current hardware. And then once we found this projection on our subspace, if the subspace is low dimensional, we can solve this classically. We can diagonalize this classically on classical hardware. And you might think, okay, well, what's the point? Because you need an exponential number of vectors to represent the ground state. This is true. But as it turns out, the accuracy converges fast enough that you only need a small number of these vectors for it to be practically useful. Yep. And so from this, once we found the description of our ground state in the subspace, then we can reconstruct expectation values on the true ground state, or the approximation thereof, by measuring expectation values on the subspace basis. So what are the takeaways, the main takeaways from this project? It's that, well, simulating nature is a very obvious use of quantum computers, simulating quantum nature, because nature is quantum and quantum computers are quantum as well. However, a lot of the interesting problems that we're interested in, so quantum materials, chemistry, stuff like that, it's still too hard for current NIST quantum computers. And so until we wait for fault tolerance, we can do, there's still some interesting stuff that we can do with NIST quantum computers. And so this is a little bit of an allegory here. So we're interested in measuring this bird behind us. So when we have fault-tolerant quantum computers, maybe we can turn around and look at the bird. But until then, we just have to look at these shadows on the wall and try to get some interesting information from that. So yeah, that's it. Thank you for listening.
Thank you, Olivier. We have time for a couple of questions, maybe. Do you have from the audience? Maybe I have one for you. I know that, well, going to utility scale problems is a challenge to identify what the right problem is. And you started with a first idea, maybe like 6 months ago, maybe a bit more than that. And then you had to pivot to something that is probably more feasible. Can you talk a little bit about this and how you changed, how you had to pivot to, and then identify something that probably is more suitable to devices that we have today?
Great question. Thank you, Justin. And so, like I mentioned, we're interested in studying mostly quantum materials. And so like a very interesting way to model quantum materials, for example, is using models, like fermionic models. And so originally we were interested in studying the Hubbard model, okay, which is a fermionic model, which is very, very hard for classical computers. And it's very interesting to material scientists, so they tell me, I guess. And so that was what we started off with in this project. But there's a problem with the Hubbard model, is that it's very difficult to map to the IBM chips. Okay, so the problem is if you have a fermionic model, it's expressed in terms of fermionic operators, and then you need to find a mapping to the actual quantum chip. And the problem is that you're limited with the connectivity of your qubits. Okay, so not all qubits are connected to all others. Okay, and this is a very big bottleneck when running NISQ quantum algorithms, is that you have to respect the connectivity of the chip. And so what we encountered when working with the Hubbard model is that the mapping was so bad that we were actually constantly swapping, doing swap operations between qubits, and this is very, very expensive. And so even for a very small scale, maybe as a reference, like an interesting problem with using the Hubbard model would be something using maybe 30 or 40 sites on the lattice. And we were running experiments with 4 sites, and this was already too difficult for the quantum computer. So we gave up on the Hubbard model, and then we switched to an easier one, which is the Heisenberg model, which has a way more natural mapping to the chip if you define your lattice in a smart way. And we're getting, so this is an ongoing project, but we're getting much better results with the Heisenberg model so far. Even though it's maybe less interesting to material scientists, for us it's still interesting and it's better. Yeah, thank you.
Great. Well, thanks a lot, Olivier. Good, thanks. So we'll go the same way we did before. Can you, well, first introduce yourselves? And this is the panel about, of course, material simulation. Well, we'll start with who you are, and then we jump in the subject.
I'm Alex, and I hope your short-term memory is better than this.
I'm Hossein. I'm responsible for quantum applications in Canada, and our Alex was not available to come here.
And hi, I'm Alexandre Foley. I'm a programmer at the Quantum Algo Lab, and my background is in, well, simulation of quantum materials. So it's yeah, it's been my thing for a decade now.
Great, thanks. We've seen a bit of quantum machine learning. Now we are talking about quantum simulation of nature, and well, it's believed that this probably is where there will be first breakthroughs in terms of quantum computing. Can you tell us why this is?
Sure. Well, the reason why is simply that it was the first idea for quantum. It's what launched the whole idea of quantum computer. So quantum matter and high energy physics are just very hard to simulate on classical computer. And well, Feynman basically threw out in the wild that, well, we should have a computer that is quantum to do that. And then it should, like, the size of problem we do solve should be about the same size of the computer. And that was the start of it. So natural quantum problem should be the first thing we successfully solve on quantum computer.
Yeah, so what I would add is that in order to do something interesting with a quantum computer, the first thing we need is a problem that is hard enough. And I'll actually talk about this. And sometimes it's actually challenging to find hard problems. In the case of quantum material simulation, it's naturally very complex. The next thing we want is small overhead in order to map that problem to the actual quantum computer. For material simulation, this is quite easy, especially for some classes of problems, to map them easily to quantum computers. And especially in the case of neutral atoms, which is the technology that Pascal works with, we naturally have a quantum material system that can simulate itself, which is kind of exactly what Alex mentioned. And this is why we think about quantum simulation with the purpose of understanding quantum materials as one of the most promising quantum applications that will probably show advantage in the very near term.
And well, just a small advertisement here. You will talk a bit more about Pascal systems just after this panel.
Exactly,
so
yes.
you
I'll talk about quantum material simulation, optimization, and machine learning, and exactly touch on the question of hard problems and what we need to do about them to hopefully see quantum advantage in the near future.
We'll try not to scoop your presentation with this panel.
Yeah, okay. A little bit of advertising is good.
Yeah, so I mean, I would definitely agree with what you both said. The only thing I would add is maybe a caveat is that us in the quantum computing community, we tend to think have somewhat of a narrow vision on how we approach problem with quantum computers, right? The tool that we have is a quantum computer, and we think about a problem that we believe is useful, and we try to map it there. But if you actually look at how these problems are tackled in the industrial setting or in a real life scenario, then you realize that there's a lot more boxes in the flowchart diagram of how you solve a problem, and not all of these boxes are going to be sped up with quantum computer. So if you're trying to solve an actual real life problem, then you have to look at the full business workflow or industrial workflow of how people tackle this problem and try to identify which boxes might be maybe sped up by quantum computer, and then work on only these boxes. I don't think it's necessarily a good approach to think that, okay, quantum is going to solve the whole problem, because these industries or institutions, they have their way of working, and they won't replace the whole thing with this new shiny tool that is quantum computer, right? It's they need to see there's an advantage for them to integrate that into their own workflow. So maybe that's the part that we're not always thinking about when we think of quantum computing applications.
Good. And Alex, you can keep the microphone. My next question's for you. You showed us a few projects that you've been working on with partners. They were from, university partners from, some places around the world. How do you, choose the projects you will work on? How do you choose your partners? How do you define projects? And from what I get, that are, maybe not most of the time, but many times in quantum simulation.
That's a good question, and unfortunately, there's not a cookie cutter selection process for projects or collaboration. Even though we're a very big multinational company, our research team, especially the quantum researcher, they really act like academic research institutions, meaning that they go to all the conferences, they had interesting scientific discussions with participants at the conferences. Sometimes they're from other companies, sometimes they're from universities, and sometimes interesting collaboration arise from that. Other times is we have, big partners that they engage in a very large partnerships with us, and they have a lot of research capabilities. So, for us, it's interesting to see what we can learn from, their expertise, because we cannot claim that we have expertise on all the topics all at once. So, we really have to, come together as a community. So, yeah.
Yeah, good. I have the same question for you, Hossein.
Yeah. I agree that we don't really have a clear process, because it's very complex to figure out what problems we want to solve and how we want to introduce new problems. What I usually do is rely on the same talented scientists that we want to work with to come up with ideas. The only thing I would really do is to define some bounds on what really Pascal is interested in. And that process so far has worked really great, because it has introduced a lot of interesting projects throughout Canada, even a few projects in US that really help us, both expand the set of use cases that we can tackle and kind of create a roadmap for the future, as well as, define a process to get into quantum advantage with some of the big applications that we have launched in, University of Sherbrooke, and also elsewhere throughout Canada.
Yeah, thanks. And Alexandre, since you've been involved in the project that Olivier has talked about, I maybe ask you the same question that I asked Olivier before. I know that you were involved in the first design of the project, then had to pivot. What would be your piece of advice here in terms of how to design a good project like that we can currently run on quantum computers?
Well, that's always a hard question, really, because current hardware is very limited, whether we like seeing it or not. There's different architecture, like Pascal architecture is very different from IBM's, and it has those two architectures have a very different set of advantages and inconvenience. So first thing, you have to think about what are the strengths and the weakness of the device you want to use. Basically, you have to design the problem with your device in mind, which I didn't do at first because I didn't know yet. And then that's not too hard. The hard part is having an interesting problem anyway. And that's where it becomes tough, because when you design your problem for the device rather than because you have an interesting problem from the get-go, well, chances are you'll land on something that's of interest to no one. So that's the tough part. I think with the Heisenberg model, that it's on the verge of something interesting. Not quite. If we do it large enough and we successfully remove some constraint, we've got something interesting. It's something that is actually used by quantum matter theorists, the Heisenberg model, with more complicated lattices than what's the natural lattice of the IBM device. But it's very close to, there's like neighboring lattices in some sense that are very interesting. So as a first step, doing the natural lattice of the quantum computer is the easy thing. But depending on the performance we get and depending on with hardware improvement, we could move on to something that is actually really tough, assuming we succeed at this step.
Then the projects that we've seen, the last three, the two that Alex presented and the one that Olivier presented, they were all projects that were partnerships between academia and a hardware provider. And we are just starting with Pascal, same idea here to work on a project. So which is again academia with a hardware provider. Do you all three think that this is the way to go for like real meaningful projects these days, or we could like think of academia by themselves thinking about good projects? So what I'm trying to figure out what ways people can use to have interesting projects these days.
I won't anger those two by saying I think a partnership with the hardware provider is a really good idea because they have the knowledge of how it works, what are its strengths and weakness, and how to adjust our problem to something that's going to work at the very least. So that's invaluable. But as academics, we can come up with a problem that they might not think of. So I see a lot of value in such partnership.
I mean, obviously, I agree with that. And I think for universities to work on their own, I mean, this is what research is in general. And the challenge with that idea for today is that the ideas that researchers try to do may not be feasible even very long in the future. There are many ideas that researchers have done in the past that haven't really been implemented or realized on any device or on anything today. But at the same time, if consider machine learning, if people only thought about what is possible with CPUs, we would not be here with machine learning today. So first, something was initiated by researchers that asked for hardwares to be created for them. And then once that happened, once that transition point happened, machine learning grew very quickly and very fast. The same thing I would expect would happen with quantum computers. One thing that we try to do at Pascal is to define projects not just based on what the current quantum hardware can do, but also things that we can implement in the future, or we think that theoretically it's possible to implement. This way, we can do more interesting stuff today that is useful for near future or even, much longer term.
Yeah, so I would add that there's a lot of collaboration between academia and hardware providers, and I think that eventually this is going to transition to be like the hardware provider is going to be a little bit phased out from the collaboration to be replaced by end user industrial players, like in the Thales project that was presented. And for a simple reason that for most projects that you're using classical simulation, like forget quantum, you're typically not partnering with AMD or NVIDIA or Intel to do your research, right? So, but you might be partnering with a end user company that would care about the outcome of the research. The reason why the hardware providers are involved a lot, as Alex said, is that we have more intricate knowledge of how you can extract the most juice out of the devices, how you can use all the tiny little tips and tricks so that you get more accurate results. For us, that means a lot of error mitigation techniques. But as time goes on, we pre-package these techniques, and we even let AI in to control the quantum computers because sometimes it's doing a much better job than humans in finding what's the best approach to error mitigation. And as we build this abstracted code, then you probably won't need us anymore. You can just trust that the code is running the right thing, and we're going to be phased out. And good example is that just backtrack 5 years ago, if you wanted to do error mitigation, then you had to implement it yourself, and you maybe put a master student only on that part of the project. And I think we save collectively a lot of time now.
And in 30 seconds, what's next for quantum simulation?
Yeah, that's a great question. I think that the chemistry results I presented is a very exciting direction. This is just the beginning of the story. I don't think this is the end for sure. So excited to see maybe what this method could do for materials, and I think we got a good shot of that with the project there. So knocking on whatever this is. Yeah, and I'm excited to see how this type of method gets integrated, and as I said, in more industrial workflows, and if eventually they find value in doing so.
Yeah, so for us, definitely the next generation hardwares that are out, trying out quantum simulation on those devices, but also having a more concrete knowledge of all tensor network techniques that are out there to be able to, fully benchmark these techniques and make sure that, when we benchmark these these simulations, we have the best answers, for foreseeable future. This is something that, all of us have tackled with in the past, and we want to have better results and better, clarity on advantage results in the future.
Famous last words?
I don't know what to add. Really.
It's all there.
Yeah.
Good. Well, thank you very much to you three. Let's thank them again with a round of applause.
Yes, it's working. Yeah. Thank you all. And thank you to the Algo Lab. This is really great event. Congratulations for that. When I arrived more than 2 years ago in Sherbrooke, I was dreaming about that, really. To see such an event on applied quantum computing, this is exactly why Pascal is there in Sherbrooke. This is exactly why Pascal is in Canada. I really believe that we can do that in Canada and to access to the North American market and to the US. So if you can go to the next slide, or maybe it's there. So I'm Raphael de Thoury. I'm the CEO of Pascal Canada, and with Hossein, that you already know now, we will introduce Pascal. And as you know, we are working on a special kind of physics approach. We are using neutral atoms to do quantum computing. And so this is an animation to show our computers. We don't need some cold for that. This is operating at room temperature. We trapped atoms with lasers. We rearrange the atoms with lasers, and we also use lasers to excite the atom in a quantum state. So it's full of lasers, and based on that, we can approach a lot of new problems, and we have a specific way to compute, and also I will introduce that more after me. If you can go to the next, there. So just to introduce Pascal, I will be very brief. I'm not doing a business presentation, so don't be worried about that. But we are very proud to be co-founded by Alain Aspect, which is just arriving now. Thank you for that. It's so beautiful. So we are a spin-off from the Paris Optical Institute, and very proud to have Alain Aspect as a co-founder. You can go to the next slide. So just to give a few words about the size of Pascal. If it's working, but it will arrive, yeah. Pascal is, I think it's maybe that one. Yeah, that's the one before, it would be better. We are reaching 300 employees around the world. Of course, the most are in France and in Europe, but we are also operating from different countries. So, of course, Canada, USA, Saudi Arabia, South Korea, and we are operating in Japan. And what is very important is that we are on the strategy to go very fast on the industrial side to be able to deliver the quantum computers worldwide. And for that, we had the strategy to open 2 factories, which is very bold as an industrial strategy. So we have now 2 factories. In fact, we are quite finishing. It's not almost ready in Sherbrooke, but we are finishing our factory I think it's just less than 1 kilometer below, sorry. And based on that factory, we will deliver the quantum computers to the USA, of course, Canada, and the rest of the world. And what is amazing to see there is that we are on the strategy to also send the quantum computers to a lot of countries that are interested to build ecosystems on what we're doing. And then just a few pictures on Canada and on strategy. We have the factory at Espace Quantique 1. It was inaugurated by François Legault just the years ago. And of course, we are on the yeah, we have the strategy to have a lot of partnership with industrials and academic partners like University of Sherbrooke, but a lot, as Hossein explained, to work on the quantum industrial application of quantum computing. And just before letting Hossein, I give you some views on what we are doing on algorithm. Our roadmap, we have published a roadmap. It was, I think, at the beginning of the year. So it will evolve in a couple of months. So this is quite an old one, but still valid. We'll focus on the technical side. We have a technical roadmap and a product roadmap. So on the technical roadmap, and maybe you've seen the publication, we have the great advantage to have a technology that scales very fast. So we are already trapped 1,000 atoms, and we are able also to rearrange them. So we are very, very about to now do full computing on the 1,000 qubits. So this is on the R&D machine that we are currently working on. And then we have on the roadmap for the 2026 and 2027 to go through the 10,000 qubits. For the addressability, it's the capacity just to change the quantum state of a bunch of atoms or maybe a single atom. So we need that also to combine what we call the analog approach to the digital approach, but also just based on the analog approach, just having the possibility to run and to excite the full system of atoms, but just to excite a part, or just to excite one, and then to do some complex algorithm, maybe combining with some HPC algorithm. That is something that creates a lot of possibility, and we are exploring that. So at the moment, we can address on the data axis. That will be soon ready for the X, and we are also on the road for the gates implementation. So 1 qubit gate, 2 qubit gates, and this is part also of the FTQC, the fault-tolerant quantum computing roadmap that we have. So we are also working on the frequency, the base repetition rate. So we are operating around something like 1 Hertz now. But of course, we need to increase that. So we are on the way to scale that and to target something that will be close to 10 Hertz in 2026. Then for the fault tolerance, I think we go fast on that. Maybe I can finish on the algorithm side. So we are also a big team on software. So we are a full stack company, and then we are developing libraries and software solutions. So we are planning to go to production, so to have a quantum development kit in 2026. So at the moment, we are currently working on developing the algorithms internally, but also with the academic partners that we have. And then on the stack, our stack, our open source stack is Pulsar to compute and to access to the computer. Cadence is also something that we launched recently, more focusing on a specific approach that we call DQC. This is something that we will run on the computer a bit later. And we will go for next year into a roadmap that we will release a lot of solvers and emulators. So some will be freely accessible, some will be open source, some will be private only for our partners. But stay tuned because we have a lot of things to deliver there. So thank you very much. I won't take so much time. I think it was much than expected. So Hossein, the floor is yours.
How much time do I have?
Oh, that's fine.
Thank you, Raph. Right. So I'm just going to continue with one thing that Raph mentioned. We recently demonstrated trapping of 1,000 atoms, more than 1,000 atoms. For that, you need a SLM system that produces more than 2,000 traps. We occupy these traps with 50% probability, and we were successfully able to rearrange about 800 of them into a desired shape, which in this case, it's a donut shape. This technology is something that has been possible in research labs for many years. What Pascal is really doing is to create modular components that can easily be installed in multiple devices, and also helps us to scale into very large systems like the one you see here. So optomechanical mesh and laser lock systems for stability and high quality of trapping. Okay, so let me just kind of explain our approach to quantum computing, because this is not a common approach to quantum computing. This is called analog control. The idea is that we have a system that naturally evolves by some dynamics, and the way we solve problems is by encoding the parameters of the problem. Whatever problem we have, we find a way to encode these parameters into the parameters of the Hamiltonian of the system. So we have a system with a Hamiltonian, and we encode our problem into parameters of the Hamiltonian. In the case of neutral atoms, these parameters of the position of the atoms and their relative distance, as well as the laser pulses that we use, the amplitude, the detuning, and phase and time of the pulse, even the time dependence of these parameters over the course of the experiment. So this is a really nice approach because, for example, if you wanted to simulate a system of magnets, the system naturally is a system of magnets, and you can do this very efficiently with little overhead, with very high accuracy of results. The downside is that you cannot solve all computable problems using this approach. So this approach only applies to a subset of things that you can do on a quantum computer. And of course, we have the digital one, which I'm not even going to explain what it is. And they can solve any computable problem that we know today. The downside is that, as we know, they're far away from actually being able to solve meaningful problems. All right, so here's my pitch today. We want to use quantum dynamics to achieve quantum advantage. It's a very simple premise, and I've already kind of touched on that a little bit. And we define quantum advantage here very simply as being able to beat best known classical algorithms on some metric for a problem that is useful. So we have a system of neutral atoms, as I mentioned, trapped in an optical tweezer. The lattice you see here is actually a result of rearrangement of the atoms. So usually what we create at first is some 50% binomial distribution of traps that are filled, and then rearrange them into desired arrangement. In this case, a square lattice. And the way we do it is by creating the traps, imaging it, knowing where they are, rearrange, and then take an image again. Then we take these rubidium atoms, and we use two lasers, counter-propagating lasers, and we excite them into a highly excited Rydberg state with something like n equals 60 or 70. So the laser has an amplitude, it has a detuning, and when we have Rydberg atoms that are adjacent, they actually interact if they're close enough. And close enough in this case is about micrometer, 5 micrometers to be exact. And it depends on the amplitude of the laser. As a result of this interaction of atoms, what happens is that the energy level of the excited state changes. And as a result, the laser with a narrow frequency is not able to excite it. And so we get the blockade effect. There's also flip-flop effect, which is when we, instead of using ground state Rydberg as a pair for a qubit, if we use two momentum coupled states like S and P orbitals, in this case, we will get a different model, which is XY Hamiltonian. So combination of these, and also, as I mentioned, in this case, I'm just going to talk about the blockade effect. And what you see at the very right is time-dependent amplitude and detuning that we apply to the system. And as a result, we get this other lattice that just popped up over there, which is, if you look very carefully, It's a subset of these atoms that are over there. So every other one is blocked. And we also see the symmetric one, which is the complement picture of the other one. And actually, we don't see a lot of other states. So that's a very a good experimental result to show that we see the blockade effect and we see this, many-body effect in our system. All right, and this idea of using the natural mode of the quantum computer. So the natural mode is that you have Rydberg atoms that interact with each other and they exclude each other from, it getting excited, and we get a many-body effect. Using this natural effect is not something that we just came up with, and it's not something that only applies to neutral atoms. So the team at Google demonstrated recently that if they allow for this analog evolution of their Sycamore system, they can get better entanglement in their system. And in just 1 year, they went from 25 to about 32, just by allowing this evolution without significantly changing the hardware or even the experiment. And for our results, this is the paper that was published quite a long time ago in 2021. And what you see is the correlation map. On the left panel, the bottom one is the matrix product state simulation, and the top one is the experiment. They have really good agreement. And the right one is a larger lattice. It's the same experiment, but it's a 14 by 14 lattice instead of 10 by 10, which is the other one. So this, if we wanted to repeat the same experiment with a gate model system, we would need 10 to the 6 with fidelity that is quite large, error rate less than 10 to the minus 6. These experimental results take a very long time to simulate. At the time, by the knowledge we had then, it would have taken 7 days for the 10 by 10, and we didn't even do the 14 by 14. And when I say we, I wasn't even at Pascal, so I'm really talking about the actual scientists who did the project. Today, these numbers will be different. We will be able to do 14 by 14 probably within a few hours. All right, so let me just talk about some of the applications we have in mind toward quantum application, quantum advantage. So the first one is amorphous solids. If you think of a crystalline solid, you have short range and long range order in the system, but amorphous solids are different in the sense that they do have short range order, but they lack long range order because of the variations in region to region. So these materials have a lot of applications in topological insulators, semiconductors, and many other quantum material applications. This is a kind of early work that we have done as a starting point for a quantum advantage experiment. The first thing we did was to create a system to generate these amorphous materials on our system. So what we need to do is to generate a layout of atoms that have short-range order but lack long-range order, and they have controllable coordination number, and they respect all the constraints that we have for implementing them on our quantum hardware. So the images you see here are generated out of a simulation that does exactly that. You can see that we can even have this coordination number 3.5, which means in some regions there are, they have coordination number 4, and sometimes they have coordination number 3. And then we started looking at these systems in 2 ways. I'm going to just talk about one of them. You can read about wave spin approximation in the paper, the study we have done on the ferromagnetic systems. When we go to the antiferromagnetic regime, we wanted to see if these systems demonstrate the same complexity as classical spin liquids. So, for example, if we take a square lattice or a Kagome lattice, we can look at something like the overlap distribution, and if we see well-separated regions, it means that if you wanted to study them with something like simulated annealing, they would be really complex, because going from one region to the other would take order n operations, which is hard to come by with single bit flip. So the left one is the square and Kagome lattice. The right one, we have these amorphous materials. The top panel is simulated annealing with a varying number of sweeps. When we go to very high ones, the purple one, we still see that there's quite a distribution of energy. It means that we haven't really converged to ground state. So these are complex systems classically. And I'm going to cut short because I'm running out of time. But basically what we have done here, we have shown that these systems are interesting. They preserve some properties from square and Kagome lattices, because they have, for example, coordination number 3, which corresponds to Kagome lattice, and coordination number 4, which correspond to a square lattice. We can also create ones that are in between, and they still demonstrate, complex properties in the classical regime. So we look forward to studying them using neutral atoms. It's not that easy because if you think about it, we have a lot of constraints in implementing this on our system. For example, the shortest distance has to be more than 5 micrometer. We cannot bring the atoms closer than this. And if you look at the variation in the distances of these atoms, if you take the smaller one and scale it to 5, then you get a lot of them that are very far away. And by using the lasers at the intensity we have today, we don't get the resolution that we want. So this is exactly what we're working on very hard to get to a point that we can actually simulate these systems. All right, so let me now go very quickly through quantum machine learning. So we are mostly interested in graphs because of the way our technology works. We can rearrange atoms in the way that looks like a graph. We can implement graphs by basically mapping the graph to the position of atoms. And there are a lot of actually machine learning techniques that apply to graphs. And probably the most interesting one is studying molecules. So classification and regression on molecules, or being able to even generate molecules, has a lot of applications in pharmaceutical and drug discovery. So one way of approaching graph machine learning is by a hybrid approach. And there are many types of hybrid approaches. There are some where you co-train the classical and quantum model together. I have found that over the years that training these models is very challenging because we don't know exactly the model for the quantum system. And that lack of knowledge tends to bias the training process. This is a different paradigm where we train a quantum machine learning model separately from the classical, and we feed the output of the quantum model to the classical model. And the idea here is to use correlations as a way to get information about long-range knowledge in the graph and pass them to a classical model like graph transformers. So this is not a new idea. Graph transformers have been around for a long time, and their idea is exactly the same. They take graphs, they create these correlation maps as positional encoding of the graphs, and they pass it to a transformer model. This is nice because you can just use the transformer models that you use anywhere else, nowadays everywhere, and pass them something that otherwise wouldn't be applying to them, because graphs have a different structure. They have varying number of nodes and structure, and it's not something you can just treat with a typical machine learning model. So the work that we have done is we've introduced quantum positional encoding, which based on quantum kernels. The idea is that we encode graphs as a position of atoms. We apply laser pulses to them, a laser pulse that is similar for all graphs. And the only difference between each experiment is the arrangement of the atoms. At the end, we read out some observables, and we calculate, for example, correlations and use them as the positional encoding of the graph. So here I'm just demonstrating what happens if you have these two data sets, class 1 and class 0. And you can see that the only difference between them is that one of the edges at the last one in class 1 has moved to left in class 0. So this is a very tiny difference between these two graphs. And if we take something like a relative random walk probabilities that you see at the top heat map, there's barely any distinction between the two graphs. But if we take quantum correlations coming out of, for example, Ising model or XY Hamiltonian quantum random walk on these graphs, we see a clear distinction between the two. This is a hand-picked result, obviously. It tells you that there is something interesting here. There's no demonstration of real quantum advantage yet. But it is something promising, and also it's a relatively easy framework to work with. We don't have two models tied to each other that is prone to a lot of errors. So one other thing we've done is that if we take a molecule like this one and we do classical random walk with 4 steps, or quantum random walk at XY Hamiltonian with different number of particles, we see that the quantum random walk is able to detect some very interesting structures. For example, it's able to detect the bottom and the top region from each other, while the classical one doesn't show this distinct difference between them. So this is something interesting also that we think these models are promising for the future. So I'm just going to breeze through classical optimization. One of the problems we can solve with our system is maximum independent set. It naturally maps to the Hamiltonian of an Ising model. We have nodes that are connected, let's say only locally. This would be similar to unit disk graph. And if we write the Hamiltonian as simply the Ising Hamiltonian of the system with atoms interacting with each other with an exclusion term, antiferromagnetic coupling, then we can map this problem very easily to our system and solve it. The plot I have here is for problems with number of nodes up to 2,000 simulated. We see that the top one done with so this is all just done with Cplex. Even if we just take the top 2% hardest ones, these are the problems you see here with unit disk graph. Even if we take the top 2%, they're nominally NP hard problems, but it only takes 10 seconds to solve them. So if we wanted to think of these problems as a way to demonstrate quantum advantage, it would be quite challenging, because with just even 1,000 nodes, we don't have actually complex problems that we're dealing with. There are ways to generate hard problems at a small scale, but with unit disk graph, it's quite challenging. And today we can address only the problems that are in this green box. So we can control the number of nodes, we can control the density of unit disk graphs, as you can see here, but for today, we're limited to this green box. So we don't even have access to the problems that are actually hard. And this is something that I mentioned in the panel discussion, that the first thing you need is problems that are hard enough. And for optimization, that's a big challenge. Another thing that I will quickly mention is that if we have arbitrary problems that are not unit disk graphs, there is actually a way to map them to neutral atoms using gadgets. The gadgets is the structure that you see over there. in using polynomial number of qubits, you can map these problems to unit disk graph. But this absolutely does not mean that you can solve these problems easily on our hardware, because by doing so, you're creating a structure that has exponential number of solutions that are meaningless. And that just makes the mapping to these problems quite hopeless. So I'll just finish with optimization, because I was able to cover the other ones, but this one I ran out of time. Combinatorial optimization is quite challenging to demonstrate quantum advantage on, because the hardware is too small today. Problems are actually quite easy. So the approaches we are taking is, of course, one of them is hybrid optimization to kind of get around some of these limitations. There are still challenges with that. We are working on multiple ideas. But another way is to get out of this combinatorial optimization paradigm and go to harder problems, for example, counting and sampling. This way, we have problems that are much more challenging for classical solvers, and perhaps they're not as difficult for quantum computers. But with that, I thank you.
Thank you very much, Hossein and Raphael, for the presentation. And this one last presentation that we have for this morning is with Stefanos Kourtis, that you met earlier, physics professor here at the University of Sherbrooke, also director of the Quantum Algo Lab. And he will talk to you about some projects that he works on using Pascal systems. So, Stefanos.
Thank you. This talk is going to be more of an outlook towards the future and a manifesto of the work that we plan to do in my research group in the coming years. So to pick up from where Hossein left off, I'm going to address problems in artificial intelligence. And as was already mentioned, there is an issue of hardness in these problems. So here I have my very own biased view of what I consider a complex problem and what I consider an easy problem. Okay. So I'm showing this slide because when we talk about AI in general, we're talking about an enormous variety of computational problems. Okay, and so they're not all equal, and they're not all equally complex. So here I show, for example, the tasks of classification and regression, which for me are easy problems. Okay, so even though we saw earlier that we can train models with billion, trillion, gazillion parameters, still in its essence, this problem is not computationally intractable. Deep learning is harder. And then as we go further down this list, we get more and more complex problems, okay? So my claim is that the problems towards the top are what is being dealt with in principle with quantum computers today, okay? And so, in fact, there on classical computers, we can deal with, as I said, millions of parameters or billions. Then, as we move further down the complexity landscape, we encounter more and more complex problems. So combinatorial optimization was already mentioned, and there we see we can easily solve practical instances with tens of thousands of variables, no problem. Now, we go towards more and more complex tasks. For example, here I mentioned inference and probabilistic reasoning, and there already with 1,000 variables, we are in trouble classically. And then going even further, where we talk about automated planning for autonomous agents, there we start to encounter difficult problems even for a few tens of variables. And so just to illustrate this, I show this task, which is autonomous vehicles that have to react to unforeseen circumstances. So for example, here, this is a view of the cameras loaded in an autonomous vehicle, and there's a green light, but at the same time, there's an ambulance coming, okay? So now we need an agent that can very snappily decide that this is an exceptional case and needs to treat it, okay, accordingly. So this, from a conceptual point of view, gives rise to problems that are triply cursed, okay? We have the curse of dimensionality, which is what you learn about first when you deal with qubits, that if I have n qubits, I have 2 to the n states. It has a curse of history because how you get from point A to point B matters in the landscape of decisions that these agents make. And there's also a curse of rarity, meaning there are certain catastrophic events that you absolutely need to avoid. And the way that AI techniques today deal with these problems is by ignoring them, okay? So the truly efficient AI algorithms, machine learning algorithms, for example, that we have, mostly ignore these problems. And this is now coming to a head where safety is actually an issue. But then if you want to include safety constraints in your algorithms, now you're making them extremely complex. And so, for example, motion planning, even in very restricted settings, goes from being in practice easy to being p-space hard. P-space is something much harder than NP and optimization problems, okay? So this is just to motivate the work that we want to do in my group, because in my group, hard problems, the hardest ones are our breakfast, okay? So that's the point of view that we take. And so we ask, what about these guys, these really hard cases? And my point of view here is that that's where I would anticipate quantum computing to shine, right? Because that's where we expect things to become intractable really fast. And the question then becomes, can we attack these problems with a quantum computer, which there we would expect to gain a lot by actually utilizing quantum computers. Okay, so before we go into encoding these problems, we have to understand what our tools are. Okay, and our tools are quantum computers. We have already done quite a bit of research in my group as to how can we encode problems that are meaningful on quantum architectures, okay? Anybody who has tried seriously to do this will find out, regardless of the platform, it is a hard puzzle to solve, because the moment you start taking a problem from the language that is native to that problem, that expresses its constraints succinctly, and you try to express the same constraints in a way that is amenable to a certain quantum architecture, you find that that description can become unnecessarily long, and so long, in fact, to the point where actually your qubits start decohering even before they have, in fact, loaded the problem instance that you're trying to solve, okay? So there is first task before you start solving problems, which is deciding which problems you want to solve, okay? And which problems on which architecture, which problems fit which architecture. And here I'm showing a couple of examples from the physics point of view, which are also fundamental questions about how how decohering qubits might affect the properties necessary for quantum computation, in this case, entanglement. And I'm showing ongoing work that we did with, I try to be fair a bit here and not preferentially mention one company versus another, okay? So I'm including two on this slide. So these are recent experiments that we did on the Quantinuum devices to trace the dynamics of entanglement as a computation with decohering qubits with a variable rate of decoherence proceeds, okay? And this is older work that we did on the IBM machines on a similar question, which is how many qubits do I have to measure before I lose a considerable chunk of entanglement from my quantum state. So with these intuitions in mind, we want to proceed further into the directions that I showed you. One area of research that we will be tackling is probabilistic reasoning. Probabilistic reasoning now, instead of asking for a configuration that maximizes or minimizes some score, asks to actually produce a probability of a certain event happening. This is a function problem, and this is much harder, okay? So it reduces to something called model counting, which is hard in general. And so our insight here is that this sort of problem is a more natural problem for a quantum computer, because when we measure repeatedly bit strings and we marginalize, say, over a few bits, we are measuring probabilities. So this is a problem that classically is expected to scale much worse, but quantumly should scale much better. And so our goal will be to develop quantum primitives for this sort of problem. Another goal is to go further down this hardness landscape and talk about planning, specifically safe planning, okay? Safe planning means that we have constraints that we need to bake into our model that make it intrinsically hard. So for example, when we talk about partially observed Markov decision processes, that's just some name, this in principle is very hard to solve. And so the insight here is that we can pack all of these curses, like all of these high dimensionalities, the dependence on history and rarity, into a problem of exploring large Hilbert spaces, for which we have pretty good understanding from the fundamental physics point of view. And now we want to take this intuition and apply it to computational problems. So I talked a bit about different architectures, and so the Pascal people before me already presented neutral atoms. So this mode of analog quantum computation might seem limited at first, but the more you think about it, the more you find ways to actually make it useful. And my claim is that this sort of language, this sort of architecture is particularly well suited for the problems that we are trying to solve. And so I also like this because my background is in correlated electron systems, and this looks a lot like what I was doing during my PhD. And so the plan is to collaborate with Pascal. This is much more bombastic than I thought it would be as a slide, but to take advantage of the ongoing collaboration and the good relationship between the ecosystem here in Sherbrooke and Pascal to deploy these problems on their processors. I'll take any questions you may have.
If you want to repeat the question.
Yeah, so the question is whether the software used to run these quantum devices should be extended to account for this sort of problem. That is further down the line, I would say, and I think the answer there also depends on the problem that you're looking at, right? So depending on how you encode your problem in a specific form, it fits better or worse to a given machine. And in my case so far, in my group, we've done this work a priori ourselves. So in my group, again, we're doing exploratory research, and we don't wait for companies to implement an API for us. Okay, so we want to attack hard problems right here, right now. Further down the line, if we prove that a certain task is amenable to quantum computation, then of course companies will probably take interest in that.
So welcome back for this afternoon session. I see that all discussions have really continued over lunchtime. That's great to see all of this happening. This afternoon, we changed topic a little bit. We'll talk about quantum in the finance sector. And to start this afternoon, please welcome Tania Belabbas, who worked with the Autorité des marchés financiers on a quantum computing for finance project. Tania?
Yes, thank you. I hope you had a good lunch. Thank you for welcoming me. I'm going to talk about quantum computing for segregated funds pricing, namely solving differential equations on near-term quantum computers. So first, I'm going to start by introducing the team. As Ghislain said, this is a project which was in partnership with, in collaboration with Autorité des marchés financiers. And the main contributor of the project was Florence Paquette, who's here, and who you're going to have the occasion to hear later on the panel. She was an intern at the Algo Lab and worked with us on this project, along with Emmanuel Hamel, who's right here, who's a data scientist at the Autorité des marchés financiers, and Alexandre Foley, who you've heard this morning, who's a quantum software programmer at the Algo Lab, myself, and also Julien, who was an intern also at the Algo Lab, but worked on mainly other projects, but contributed in a little part where he ran some experiments on real devices, which implied some optimization and everything, so he worked on that. Okay, so what's the project? In one sentence, segregated funds pricing at maturity with annual reevaluation of a guaranteed minimum maturity benefits. So a lot of terms, I see people in finance here in the room, but for other people, maybe these terms are not really familiar. So I'll take a short moment just to introduce every one of these aspects, starting with segregated funds. So a high-level definition of a segregated fund would be an investment product that is offered by insurance companies and that include an insurance guarantee component, so that offers a certain protection. Different kind of protections exist, but I'll go on that a little bit more later. And they also include a maturity date. So for example, we can talk about 10, 15, 20 years. So you can see it's on the long-ish term. And at the maturity date, you receive whatever the funds can provide. So I talked about guaranteed minimum maturity benefit. What is this? It's a type of guarantee that allows you to protect, that allows a protection of the investor's capital. So as I said, with segregated funds, there can be different type of guarantees. This is one of them. And at the fund's maturity date, the investor will receive at least a guaranteed minimum amount. So this is where the insurance guarantee component is for the GMMB. And for example, again, it's still 10, 15, 20 years. And yeah. So let's go over a small example to illustrate all of this. I think it's going to be a bit clearer. So let's say Alice is looking for a long-term investment option that offers both potential growth, but also a certain protection on her initial investment. She could decide to invest in a segregated fund with a GMMB. What does that mean? Well, if she invested $10,000 in the beginning, she'd have a certain maturity date. Here, for this example, it's 10 years. And then she'd have an initial investment amount that is guaranteed. And in this example, it's the $10,000 that was initially invested. That's usually the case. And then at the maturity date, so at the end of the 10-year term, she could receive either $10,000 or more. But the guarantee aspect comes from the fact that she has at least $10,000 at the end of the 10-year term. Of course, she would want to have more than that, but that's a detail. So if we look a bit at what could the market evolution look like, so in the blue curve here, we have the fund value. And in the green curve, we have the guarantee. Something I hadn't talked about before is that the guarantee is, for example, here reevaluated yearly, which means that every year we look at the guarantee price and we look at the blue curve, which is the fund value, and we look at the difference between the two and we take the maximum between the two, which means that, for example, at year one, the guarantee here in the green line was higher than the fund value, so the guarantee doesn't change. But if you look at year two, for example, the green line goes up because the fund value becomes the new guarantee, and so on and so forth. So the fund value could reach very low value or very high levels, but the guarantee is evaluated once every year. So at the end of the 10 year, in this example, Alice would gain a bit of revenue here because of the use of her segregated fund. Okay, so that's the context. And I'm gonna put a bit of math on it, but really not that much. So let's say we say the variable ST is the segregated fund value at time t. And we have GT that for us is the guarantee value at time t. Then the guarantee value at a certain time t is given by the maximum between the segregated fund value and the value of the guarantee at the last point of time. Right, that's exactly what I was showing with the curves. And in this case, t would be 1, 2, 3, up to 10 years for Alice because her maturity date was up to 10 years. Again, this is yearly reevaluation, which is why we have 1, 2, 3, etc. So we initialize the cost of the guarantee price for the segregated fund reaching the maturity by this formulation right here, where C of t is equal to E, and E is the expectation value of this value in here, which is the maximum of between the two distribution, and X is a random variable. So basically, our cost here is describes whatever the insurance company that provides the segregated fund is expected to pay at the end of the maturity date. Okay, so an insurance company would want this value to be lower. So this allows us to estimate what price should the guarantee be, basically, at the beginning. Okay, so if we look at a bit of a literature overview, techniques for estimating the value of C of t exist. Classically, we talk a lot about Monte Carlo methods that estimate the trajectories of the model. And the problem with these methods is that they can get quite costly for simulation on long periods. And we're talking right now about long periods, 10, 20 years, etc. So here, our point of view was that quantum computers allow us to use a wave function, and a probability distribution can be generated on a quantum computer, and we wanted to apply manipulation on the wave function such that it corresponds to the probability distribution of C of t. Then, naturally, measuring this probability distribution returns the expectation value that we wanted to have in the beginning to allow us to do segregated fund pricing. So again, looking at the literature, we have methods of amplitude estimation or phase estimation methods, quantum Monte Carlo, etc. that exist, but this method generally do not work on near-term devices, and the focus of our work here was really near-term methods. So we're talking about few qubits, short depth of circuits as much as possible. And we chose to work on methods based on differential equations. So what we're doing right here is every time, we write out equations, differential equations to model our problem of segregated fund pricing. And then we want to use a quantum computer to solve this differential equation, so to evolve the model and obtain a certain result that then could be used to have C of t. So to do that, we have selected 3 approaches, and actually 2 of them were explored during this work which was last summer. One of the method, the first one, is looking at the log price density simulation. So we expressed a model that used the log price of the fund value, and we were able to evolve it using an algorithm called VARKite. So VARKite is variational quantum time evolution, for those of you who know it. And basically the framework that we developed was you receive a certain classical model with differential equations. We translate it to a Hamiltonian that we can then use as an evolution operator, while using a principal variational principle. So we evolve it. We evolve that during, for example, a year, and then we apply a circuit which allows us to compute the maximum between the guarantee and the evolved segregated value. And this method was our first doorstep into this whole problem, and turned out to be a bit limiting in terms of number of qubits, because every time you apply Vorkite, you evolve a year, and then you compute the maximum, etc. It becomes really heavy in terms of number of qubits. It doesn't scale as good, at least in the way we implemented it. Maybe there is another way that we didn't see. So we tried another method which was maximum density simulation, where the equations that we evolve are actually equations that include the computation of the maximum. So the maximum is computed implicitly, and this method turned out to be quite unstable numerically, so it didn't give us necessarily good result, contrary to this one, which gave us good result, but was hard to do on 10 years, etc. We did it on 2 years, actually. And it turns out that this method, when you take the models that we use and you evolve them even classically, it's also unstable. So we rapidly discarded that. And finally, I wanted to just give a word about the look-back method, which we have written out the math. We have the Hamiltonian. We have yet to implement it. This comes in future works with Florence, Professor Anne Mackay, and Emmanuel, which we think, and I'll show you this here, it is very promising. It is stable numerically, and it wouldn't scale with n qubits register per evolution year. And we have very high hopes for this method, and I can't wait to implement it with everybody. And about approach one, we wanted to maybe think a bit about the scalability and the generality of our algorithm, and maybe find a method that doesn't make it so that the numbers of qubits scales so much. But this is, I think, the overview of the project. Thank you.
Thank you very much, Tania. And to continue the discussion with this, Flash roundtable, we'll go with Professor Anne Mackay from the Department of Mathematics and also at the Management School, Emmanuel Hamel de l'Autorité des marchés financiers, and Florence Paquette, who's a student in the Quantum Information Science bachelor's degree here at Université de Sherbrooke. So please join me. So welcome to this panel discussion, and we'll go with the now established way of doing things. Can you, first introduce yourselves and tell us maybe where you're from?
Yeah, for sure. So my name is Emmanuel Hamel. I'm a data scientist. I'm working at the Autorité des marchés financiers. The Autorité des marchés financiers is, for those who don't know, is the financial regulator of the province of Quebec. So we're like the police of the financial market in Quebec, but we're not really the police, but I think it's a good image. And I'm working in the research lab of the Autorité des marchés financiers. So I'm in a full-time research position, and I work on AI models, actuarial models, financial models, and I also have a project with the Algo Lab on the quantum computing in this project, but was presented by Tania before. And my background, I have a bachelor, a master, and a PhD in actuarial science. So basically, that's it.
Hi, my name is Anne Mackay, and I'm a professor here in the Department of Mathematics and the Department of Finance. My research is mostly on, I've done a lot of research on segregated funds, so long-term financial guarantees. I've looked into numerical methods to price that kind of investment vehicles, so it makes sense to now look at quantum computing to price them. My background is also originally in actuarial science, which makes it also easy to work with Emmanuel. And I've been working on quantum computing projects for finance since 2021. So I'm starting to have a bit of a good overview of what we can do there.
Hi, everyone. My name is Florence, and I'm a third-year student in quantum science information degree. And this summer, I had the opportunity to intern with the Algo Lab and with the Autorité des marchés financiers, of course. And I worked on the project that Tania just showed you for the whole summer.
Good. So can you tell me and the audience here, what do you see in terms of research right now in quantum computing applied to the finance sector? Is it just to segregated funds, or like what are the types of projects we can think of in terms of using quantum computing?
So right now we have a few projects actually going on. Here at the university, what we've been trying to do is mostly price financial derivatives. Financial derivatives means you look at the price of an asset on the market. Well, I guess some of you are in finance, you know, but for the others, yeah, you look at the price of an asset on the market and you look at a function of that price. So maybe it's a contract that's written on that asset. And then we try to predict those moves in the financial market. And from those predictions, calculate the price today of a contract on these. So we're looking at different types of such contracts. Some that involve optimal stopping also. So that's what we've been doing here. There's also a bit, so it's a bit financial, but it's also a bit actuarial. We're looking at certain ways to calibrate models more in the field of insurance. So where you have a bit less of markets and long-term stuff, but a bit more statistical questions. And in general, just to give you an overview of what's being done maybe outside, like the papers that we've read, I think that, or what people say quantum computing could be used for in finance is also portfolio optimization, because we know that quantum computing would help with optimization. And so use it for quantum, for portfolio optimization. Maybe you have something you want to add?
Yeah, so what interests the Autorité des marchés financiers in looking at quantum computing? That may be the question.
Yeah. In general, so it's an important topic for us. First, for the cyber security issues. So we want to have a close relationship with the universities and the Algo Lab to have a better understanding of how of the risks. So that's one main point. The second point is we want to have a better understanding of how the financial institutions could apply quantum computing inside the companies, and to have a better, so it helps us to have a better understanding of the risks. And I would say the third part of the answer is that the quantum computing could help us to solve problems, calculation problems that we have as a regulator. For example, in practice, the calculations for the variable annuities are very computer intensive. And even for some calculation, it takes a couple of days for insurance company to produce one result with either at hundreds or thousands of cores or many GPUs. So if we could be able to perform this calculation much more quickly with the quantum computer, that would be great. So that's the main reasons, I would say. Yeah.
Good, thanks. Florence, my next question is for you. I was listening to Tania's presentation, and of course, on a daily basis in the Algo Lab, we talk about qubits, we talk about all the math and the science that goes around the quantum computing. You've been studying for 3 years now in quantum information science. What about learning finance for doing your work in quantum computing? Because I guess that was not your prior knowledge. So how did it go?
Well, of course, it was a challenge because I came into this internship with basically no knowledge in the financial fields. But I had the luck of having Emmanuel, that was a very great help and a very great mentor. And he taught me a lot about finances, and also Alexandre, which is standing over there. They both helped me a lot to learn about finances, because it is complex and it was not easy. But with hours of reading and asking questions and trying some things, I figured it out. I figured a little bit of it out, not everything, but I learned enough to be able to work on this project. And also being able to understand the differential equations is a big part of it, because I had to basically replicate them, if you can say, on a quantum computer with quantum circuits. So with their help and learning how those differential equations were working, I was able to with their help, implement some algorithms.
So at the end of the day, do you think of your project in terms of the financial aspects of it, or do you think of it as the mathematical structure behind?
Both. I think both, yes.
Good. So what about what comes in the next months? And because we've talked about like next projects, it's been mentioned in the presentation earlier. So what's coming?
Maybe I can start to answer and then you can complete. But Tania presented the look back method very briefly, but it's something that we want to explore because, as she said, we think that it's a promising approach for maybe simulating more realistic models, because the model that we have right now is very basic. It's a good model, but it's not very realistic. So if we want to be able to simulate more realistic models, maybe we have to look at another approach, and the look back method would be a pretty promising approach. And also the approach that we have right now, as Tania said, it's not very general. So we have specific algorithms to simulate the 1-year evolution and the 2-year evolution, but we cannot generalize that for example, 10 or 20 years. So I think it would be very relevant to look more into this approach to see if there is something to do with generalizing this approach.
Yes, so also another important point is that the actual implementation of the Varkate algorithm in the AlgoLabs library is with a fixed Hamiltonian on the time period. But for a more practical implementation, we need a Hamiltonian that can change with time. And this winter, we will continue the research project with Florence for another 8 months. And the first part of the project will be to implement a Hamiltonian that can change with time. So with that, we will be able to consider more realistic hypotheses and use the third approach that we mentioned. Because the annual guarantees, the way we implement it is by changing the boundary conditions every year when there is the guarantees, there is a reset of the guarantee. So that you need a different Hamiltonian at this particular point in time in the differential equation. And to have a Hamiltonian that can change over time will also help us to implement other financial products or insurance products. We could develop algorithms for other insurance products to implement it on the quantum computer with Hamiltonian that can change over time. So that's what I see coming.
Anne?
Yeah, so just, I think they've already given some pretty good elements of response, but just to add to this, first of all, I think that we have a great team to continue this project. We're very lucky to be working with Florence. She's got this training from the undergrad degree here in quantum information science. It's the first time that I'll be working with a student from this program. That means a student who's really trained in quantum computing, which I'm very excited about. We have, Emmanuel has been working also very hard on this topic, and the IMF is very interested in quantum computing. And also, I think that the tools that we can develop here, I can see links with other projects that I'm on quantum computing for finance. So what we'll be developing here, we'll be able to apply to, for example, to price other types of derivatives and all that. So yeah, I'm very enthusiastic about this project.
Great, thanks. Maybe just a little word to say that, Florence, this is your, is it second or third internship that you'll have? Third, yeah. Second official, but third one in reality. Because this last internship in the program is a 8-month internship. So this is why we're talking about this period of time that is coming. So it will give you the opportunity to really jump into the project for like quite a bit of time. And we are all looking forward to see what will come out of it. That is for sure. And I'm coming back to the last thing you said. You opened a little bit on what could be next after this project. So can you all you three tell me more about what you see as next steps, but not just for this project, but then what's coming in the next months?
So I have we have a few students, so a few smaller teams that are working on different projects. Do you want to hear just a little bit about them?
Yeah, absolutely.
So in particular, we're looking at pricing. So I'm interested a lot in American options. So that's a kind of derivatives that involve a problem in mathematics called optimal stopping, and it's not trivial. We're looking into ways, just how can we price this on a quantum computer? And I'm not telling you that we're going to be able to beat classical computers now, but at least we want to explore that. And it's really not an easy topic. So that's one thing we're doing. And at the same time, like I was saying, we're working on a project in the insurance field. So we're trying to calibrate a model for, it's a pricing model for car insurance. So that's very, very different. We're using completely different tools, but there's some ideas there that are very promising. All of this we're doing in collaboration with the Algo Lab, and they are absolutely essential for us. Like this collaboration is necessary, or we wouldn't be able to work on these projects.
Great, thanks. Emmanuel, on your side, what's coming? What do you see in your crystal ball there?
Yeah, from my point of view, I would see more work on the segregated funds, but to add more realistic hypothesis one step at a time. So now we have like a certain model for the fund value we could add, and the volatility is deterministic. We could add a stochastic volatility and add other stochastic component so that the model is closer and closer to what the actuaries are doing in practice. So that would be what I would see the future extension to be. So to have a model that is closer and closer to what the actuaries are using in practice. That would be how I would see the future.
Yeah, go for it, Anne. Yeah.
That reminds me, maybe in the long term, the way that I see quantum computers would be used for what we do is that they can be used for specific subroutines that are too slow. For classical computers, if we can identify those subroutines that can be sped up by the use of quantum computers, then it's really this hybrid framework that would be optimal, I think.
And for the project that I worked on, we mentioned that the first method takes a lot of qubits, but in the long term, that wouldn't necessarily be a problem. So this method could apply in the long term because the number of qubits wouldn't necessarily be a problem. And also on my side, I would like to continue in the long term to explore this field.
Great, thank you very much. Well, what I get from the discussion is that you have hard problems. Coming back to what Hossein said this morning, it's not necessarily easy to find hard problems to study with the angle of quantum computing. It seems that the financial sector has such problems, and this is why it's so interesting listening to all of you. We'll talk a little bit about this this afternoon. Thank you very much, and let's thank them. Please welcome Denise Koch from Calcul Québec. Denise is going to talk about what are the exciting news on Calcul Québec's side with an announcement that was a little earlier this fall of a quantum computer that is located at ETS, that is called Monarch. So we will learn more about what Monarch is all about right now.
So as was said, I'm here to talk about our recent acquire of quantum computer, which is called Monarch. I'm going to get into details into that during our presentation today. So first, sorry, sorry about that. So first of all, I'm going to introduce Calcul Québec. For those of you who do not know us, we are a non-for-profit organization that offers advanced research computing to researchers in Quebec, but as well governmental institutions, as well as a few clients from the private sector. So many of our partners here are most of the universities here in Quebec, as well as a few CEGEPs. And our main financial partners are the government of Quebec, as well as the Digital Research Alliance of Canada. So what I mean by advanced research computing is that we offer high performance computing infrastructure, as well as services mainly geared towards research. So all fields of research that we represent, be it math, humanities, science, of course, we have the infrastructure and the software to help researchers utilize high performance computing. So we offer the infrastructure, the computing clusters, we offer cloud computing, data storage, as well as interactive notebooks for teaching. We offer extensive documentation on the large stack of software that we offer to the research community. We offer training as well as support to how to use our advanced research computing infrastructure. And now we are proud to be able to also offer to the community quantum computing. So to talk a little bit more about our infrastructure, we have two large classical computing clusters with over 100,000 CPUs and over 1,000 GPUs that we offer to the community. And we have a recent addition, Rorcal, which is going to be available very soon. So we are continuously renewing our infrastructure in order to be at the forefront of what we can offer to the community. And we recently acquired a universal quantum computer, meaning that it is a computer that is based on circuits and logical gates. That is called Monarch and has 24 superconducting qubits. So just to look a little bit at the difference between high performance computing and our quantum computer, here we see rows of high performance computers that are within our, which are situated at the École de Technologie Supérieure in Montreal. And here I am showing our quantum computer. Wait a minute, right here, which is called Monarch. So we see that we have two very different types of infrastructure for the quantum computer and the classical computers. Here we see both of them together. So here we have Narval in the background, our high performance computers, and in the forefront here we have Monarch, which is a quantum computer that comes from Anion Systems in Montreal. So it is a Quebec-based quantum computer that we see here, and I'm going to show shortly the components of this computer. So here we are. It is a cube that has 4 modules. You may be familiar with various quantum computers before. There are 4 main modules. We have an electronics module, a service module, which are to be able to control the qubits within the machine. We have a gas handling system because the quantum processor needs to be at around 15 millikelvin, which requires the use of helium-3 and helium-4 to to be able to cool down. And of course, here we have the cryostat module, which actually contains the quantum processor, which I'm going to show right here. So if we remove the outside shielding from this computer, here we see the quantum processing unit, which is just this little chip right here, but requires all of this external service modules in order to actually be able to work. So these superconducting qubits, they use microwave pulses in order to control the state or the phases of the qubits. And all of this structure here is in order to control the quantum processor with the 24 qubits that are present there. Okay, so the processor is very, very small. It's about 2 centimeters by 2 centimeters, and it contains 24 qubits shown on the mapping right here. Each one of these qubits has a few lasers tuned onto them in order to control the state of these qubits. So why would we use Monarch? So first of all, Monarch is a near term, as was said earlier, a near term type computer or a noisy intermediate scale quantum computer, okay? Meaning that these computers have a lot of noise, and the more qubits you have, the more noise that accumulates. So it is not possible to actually perform large algorithms on a large number of qubits because each qubit has a certain level of noise and also a time to which the qubit stays in a coherent state. So when we say a coherent state, is that each qubit needs to have a phase change, of course, all of you know this, and it can only stay in that state for a certain amount of time. So you need to be able to perform circuits quite rapidly on these computers within the coherence time of your quantum computer. So why would we use a quantum computer with very few qubits at this time? It's in order to, first of all, be able to test and develop algorithms, be it like the ones that were shown just today, or error correction type algorithms. So it is useful to the community for the development and testing of new algorithms. Another reason why we would use Monarch is to study hybrid quantum classical algorithms. One of the main advantages of having a quantum computer at Québec is that we can directly integrate the quantum computer into the high performance computing clusters, or not integrate within, but have a full integration of those two parts. So we can send a portion of a job to the classical computer, send, for example, an eigenvalue finding algorithm to Monarch, bring back the results, study those results or optimize them, and resend the parameters back to the quantum computer to obtain a new set of eigenvalues. So the idea here is to be able to strengthen the hybrid quantum classical possibilities for the future of quantum computing. So another reason why we would use Monarch is to be able to study fundamental physics or fundamental chemistry of systems, of small systems that we are still looking to understand the fundamental properties of. So quantum computing is very well adapted to natural quantum systems. And also, Monarch is there to be used to train and to help develop the new generation of researchers and trainees for the development of quantum computing in general. So we offer training as well, but we also offer the possibility of using Monarch for professors who wish to use Monarch for teaching purposes for quantum computing. So we have a number of projects that we are working on within the team at Quebec. As I said earlier, we are working on integrating the quantum computer very seamlessly into our high-performance computing infrastructure. So our first, we have two main projects at this time. And of course, we're going to be developing even more projects in the near future. So at this time, the first level of integration of Monarch with our high-performance computing platform is what is to be able to have the language, the native language of Monarch, which is Julia. So the native programming library for Monarch is called Snowflurry, and it is written in the Julia language, programming language. But as you all know, most of the quantum computing software packages or simulators are written in Python. So one of our first goals was to be able to bring this Snowflurry into a language that is more accessible to the community. So we are developing a plugin that goes in between Python-based platforms and the Julia-based language, which controls Monarch. So we have chosen to do a bridge between Python and the Julia-based language with the software suite Penny Lane, which is a program, a quantum computing simulator based for quantum machine learning, but also offers variational quantum eigensolver and optimization modules. So it's a very, very complete software platform for developing quantum computing algorithms. It also has a lot of documentation and examples available. And it is developed by a company called Xanadu, which is a Canadian-based company. So Penny Lane offers already plugins that allow to use Qiskit, for example, which is one of the main simulators that is used today. Qiskit, Cirq, Amazon Bracket. It allows plugins to go and be able to use each one of those quantum computing hardware platforms. And that is why we chose Penny Lane as the basis of developing a plugin which allows people to be able to use Monarch directly. So you could program in any simulator that you are familiar with, and via plugins from Penny Lane or from us, you can simulate directly on our high-performance computers or directly go to perform calculations on Monarch, the quantum computer. One of our second projects is to develop a highly optimized transpiler. So a transpiler, what it does is that it takes the logical gates from our circuits, our quantum circuits, and translate them into native gates that are understood by the quantum computer. So changes the logical gates into actually instruction for the microwave pulses, so directly rotations to the qubits. And our goal here is, of course, Snow Flurry does come with a transpiler. It does do this translation of the quantum circuits to the native gates. However, it does not do any optimization of those circuits. So as I said, Monarch has a set of 13 native gates, okay, which correspond to rotations or direct microwave pulse frequency instructions to the qubits. So the first step of a transpiler is doing the translation of the logical gates to instructions that are understood by the electronics within the quantum computer. However, there is no optimization as to where these instructions are going to be mapped onto the quantum processor, nor is there any optimization of the circuits that are used. As we know, in the NISQ era of quantum computing, we want to reduce the depth of our circuit, so reduce the number of instructions as much as possible in order to streamline the circuit and obtain results that are the less noisy as we can. So one of the goals of this transpiler is to be able to reduce the size of the circuits, as well as to optimize where the circuit will be run on the quantum processor. So at this point, the transpiler will choose the qubits that are the least noisy, but may not choose the qubits with the most efficient nearest neighbors for different types of circuits. So developing this transpiler allows us to, first of all, commute, so do the translation of our circuit into native gates, to merge some of those gates that may appear many times within the circuit, and to finally do some cleaning up of all of those native gates in order to reduce the final circuit size or circuit depth of your calculation. So those are some of the projects that we are working on right now. And in the future, we are working on trying to fully integrate, for example, our GPUs with the use of the quantum computer Monarch. So we offer a number of services. We are a team of 7 members at Calcul Québec, and we offer a number of services to the research community. So our first service, as mentioned earlier, is first of all to offer access to Monarch to the community. Monarch is right now in the test phase within our facilities. It's going to be open to research coming very soon in the beginning of the year. And we offer support for any type of possible quantum simulator that you may be interested in using for your research. So we have the background software. We offer Qiskit, PennyLane, Cirq, many of the simulators that are available right now. And we will be helping the community in order to use these simulators, as well as port them towards use of the quantum computer Monarch. So one of the services we offer as well is software development. As we said earlier, we have a number of pilot projects. So some of our projects involve being able to integrate, for example, error corrections within our transpiler or our penny lane plugin in order to provide some sort of correction for the results that are attained from Monarch. And one of our pilot projects is as well integration with our high performance computing, as I said many times. So we also offer user support. So we have a team of analysts that offers that we have specializations in many fields of quantum computing so that we can help researchers integrate their projects or research projects. We develop documentation online, and we offer a number of workshops on theory and on programming for quantum computing. And so our team of researchers, our team of analysts, and our team of software developers here that we can be reached at quantum@quebec.ca if you have any needs for our services or for consulting. So with that, I say thank you.
Thank you very much, Denise. So I guess if you have questions for Denise or the rest of the team, there's a few people here from Calcul Quebec. You're welcome to ask them during the 4 to 7 a little later today. Our last presentation of this afternoon before we go to the breakout rooms will be from Etienne Lord. He's a research scientist in digital agronomy and AI at Agriculture Canada. So Etienne's working on exciting quantum computing projects, and we will hear more about that right now.
Good. Thank you. So I'm a researcher in computer science. I do mostly digital agriculture. And today I will present you the QRDI project that we talked a little bit with the panel this morning. I'm the principal PI for this project. And this is a joint project from AFC and Anarcan. Good. So digital agriculture, what is it? First, we need to go into the background, what we are trying to achieve right now in agriculture. And this is the digitalization of agriculture. We are preparing the next step to go into robot in our field, a lot of IoT, some predictive analytic. And to do that, we use a lot of data, right? This is just one example of one of my projects. So we have robot in a greenhouse. We take a lot of data, hyperspectral and infrared, and we try to create those deep learning models to try to predict some disease, to predict some stresses to the plant. And after we create those models, we transfer them to the robotic platform. Right now, there's not a lot of them in the field right now, but we are preparing for the future. So this is just some example of what we are currently doing. And in the far right of the screen, you see, for example, some application of those models. So we can map some specific disease, some specific prediction to crop in the field, either horticulture or for cash crop like corn and soybean. Good. So the QRDI project, in fact, is a 5-year project in collaboration with, like I said, Anarcan. And the goal is to bring predictive analytics on some of the data projects that we use in the government for Earth observation. So for example, AFC, we have different projects that we use daily, either for the government to do some prediction in terms of exportation. So we have some crop classification. We have some projects that try to estimate, for example, or predict the yield of some of those crops. And we have also some projects that try to do biovigilance. Biovigilance is the fact that we try to predict if a specific pest is going to appear in a specific field or region. And well, we have different kind of AI network that we use for that. And also, we also have the project with Anarcan, which is in flood forecasting. So out of this data project, use big data. And so training the model right now is a big burden. We use a lot of the GPSC computation software and computation node to create those models. And we try to look into using quantum to upscale those models, maybe have some better predictive power, but also to be able to at least train those models faster. So the goal of the project is really fourfold. So we want to use real world data set that we use in agriculture. We also want to evaluate the challenges in terms of translating some of our predicting software to quantum. We want to train some ID qualified personnel. And we also want to try different quantum systems to not be restricted to one computer or another. So to do that, we develop what we call a benchmark. And this is really the center of this project, is to create this kind of benchmark with real world data set. For example, here you see a real world data set of some clustering of satellite data for some different crop. And what I'm showing you here is some work we did this summer with a student from the university, from the ETS, and a student from the University of Waterloo that tried to tweak a little bit what we can already do with Qiskit, but apply it to real world data. So as you can see from those results, for binary classification, it's not too bad. So quantum computer can do real work. It's just right now we are just starting to, we still need to tweak a little bit the model. But as you can see here, real world data is messy. It's really tough to do some real clustering on this data. So it's just a first step. And this is an example of some of the data. It's more complex than that because this is 3-color images. Normally we use a lot more channel of color. But as you can see, it's kind of challenging to classify even for a human, those kind of data. So another work we do is really to challenge those quantum computer. And what we did last summer, the project is a 5-year project. We started in 2023. And what we did is just quantum image encoding to see what is happening on a real world quantum computer. And I think we talked a little bit about it in the presentation before me. But if you try to run those simulation on a real quantum computer, you are hit by the number of gates that you use. Still, for us, it's really good because we are trying to create a benchmark to see what will be happening in the future with some real quantum computer. So I just, this is really just some illustration of those processes. So as you can see, if we simulate on a real quantum computer or run it on a real quantum computer, it's pretty good if you are below 5,000 gate. But as soon as you hit this 5,000 gate limit, we were met with a real mess in terms of image encoding, right? So there's still some work to be done, but a lot of our data in agriculture and in computer science are matrices. So this is for us the first step, to encode this data for practical use. We were talking today about some practical problem, trying to find some hard problem. Well, agriculture is a hard science. We have some really hard problem. Just thinking about the microbiome that we are trying to understand in the soil, if we are trying to tackle problem in transcriptomic, proteomic, genomic, metagenomic, it's really difficult to achieve those computation even on the current computing cluster. We can put some hypothesis, but to really simulate those systems, it's really complex. Protein and chemical structure, well, we see now with ChatGPT or ChatGPT like that we are achieving another level for those prediction, but still it's not perfect. So I think with quantum computer in the future, we can do something with that. And animal breeding and welfare, well, we don't think a lot about those, but we do a lot of breeding in Canada. We have a lot of data on animal welfare, but processing all this data is really challenging. So if we can achieve at least just a small part of it using quantum computer to speed up some of the function, for example, computing some kernel, I think we'll achieve a lot of good for animal welfare and also for the industry in Canada, for the producer. So on that, I conclude, and this is my lab. Normally I'm in the field, but I'm also doing some quantum computing, and those are my students. Thank you.
Thank you very much, Etienne. So that was a great presentation, knowing more about your projects at Agriculture Canada. Now for the rest of the day. First thing, I would like to thank many people for this event, for having happened. First of all, of course, Tom Mala. Please have him a big round of applause. Tom has been in touch with all of you. He's the one behind all the logistics of the day, which went pretty well. And maybe aside from this mouse there, but we won't talk about that. Please don't mention it in the evaluation form. Otherwise, I mean, it was just a perfect. I don't know if you agree with this. Yeah, well, thanks a lot. I would also like to thank, again, District for having sponsored the breakfast here. More generally, the MEIE, Ministry of Economy, here in Quebec, that is behind the Algo Lab for many, many years now, like 5 years. We also, I would also like to thank, of course, all the presentators of the day. It was great having you all here. I think it's 16 people that came by the stage and talked to you today, which is kind of, again, of a great lineup. The whole team of the Algo Lab, some presented, some are behind the scene, well, today, but they were all there for the makeup of this day. So now what's next? We have some people that have registered for the reading groups. You have been in contact with Tania if you are in those reading groups. If you don't know what I'm talking about, it's perfect. There is still one more group I will be hosting. And we will go in the other pavilion over there to talk about, well, the Quantum Algorithm Alliance that is being formed. And more deeply, we'll talk about quantum training. And there I have many questions for you. So it probably is more toward people that are either in the industry or other organizations that are interested in those topics. The people that are in the reading groups, you already know where to go. You stay here, kind of easy. And you'll get all the rest of the instructions afterwards. If you are a grad student or a professor with an interest into those reading groups, one is in quantum simulation, the other one is in quantum machine learning, you can contact us, either I or Tania, who's in charge of those groups. If you want to participate in either one of the groups will start their real work, actual science work by January. So without further ado, I guess that we will go for these breakout sessions. Come back here around something like 4 for the beer time. It's the happy hour by then. If you're online, thank you very much for having been with us today. And people that are coming with me, we will meet upstairs over there so that we can all go to the right room in the other pavilion. On that, thank you very much.